The emergence of quantum theory is linked to a well-known phenomenon that does not belong to the central sections of atomic physics. Any piece of matter, when heated, begins to glow, and as the temperature increases, it turns red and then white. The color is almost independent of the substance and, for a black body, is determined solely by its temperature. Therefore, the radiation produced by such a black body at high temperatures is an interesting subject for physical investigation. Since this is a simple phenomenon, it should have a straightforward explanation based on the laws of radiation and heat. An attempt at such an explanation, made by Planck and Jeans in the early 19th century, encountered serious difficulties. Unfortunately, these challenges cannot be explained using simple concepts. It is sufficient to say that the sequential application of the known laws of nature at that time did not yield satisfactory results. When scientific pursuits led Planck to this area of research in 1895, he sought to emphasize not the problem of radiation, but the problem of the radiating atom. Although the shift towards the radiating atom did not eliminate the serious difficulties, it made it easier to interpret and explain empirical results. Just at that time, in the summer of 1900, Carl Ebohm and Rubens conducted new, extremely precise measurements of the spectrum of thermal radiation. When Planck learned of these measurements, he attempted to express them using simple mathematical formulas that, based on his study of the relationship between heat and radiation, seemed plausible to him. One day, Planck and Rubens met for tea at Planck's house and compared Rubens's results with the formula that Planck had proposed to explain Rubens's measurements. The comparison showed complete agreement, thus leading to the discovery of Planck's law of thermal radiation. For Planck, this discovery was just the beginning of intensive theoretical research. The question arose as to what the correct physical interpretation of the new formula was. Since Planck could easily interpret this formula as a statement about the radiating atom known as the oscillator, based on his earlier work, he soon realized that his formula appeared as if the oscillator changed its energy not continuously, but only in discrete amounts, and that it could only exist in certain states, or, as physicists say, in discrete energy states. This result was so different from everything known in classical physics that at first Planck seemingly refused to believe it. However, during the most intense period of work, in the autumn of 1900, he finally came to the conviction that it was impossible to abandon this conclusion. As Planck's son asserts, his father told him, as a child, about his new ideas during long walks around the city. He explained that he felt he had either made a first-rate discovery, perhaps comparable only to Newton's discoveries, or he was completely mistaken. At the same time, it became clear to Planck that his formula touched upon the very foundations of describing nature, that these foundations would undergo significant changes and alter their traditional form into something entirely unknown. Being conservative in his views, he was not at all pleased with these conclusions. However, in December of 1900, he published his quantum hypothesis, the idea that energy can be emitted and absorbed only in discrete quanta of energy. There was hope that it would not go beyond the traditional boundaries of physics, but this turned out to be in vain. Significant features of Planck's attempt to reconcile the new hypothesis with old notions of radiation took about 5 years before the next step was made in this direction. This time, it was the young Albert Einstein, a revolutionary genius among physicists, who dared to move even further away from old concepts. Einstein found two new problems in which he successfully applied Planck's concept. The first problem was the photoelectric effect, the ejection of electrons from metal under the influence of light. Experiments, particularly those conducted by Leonard, showed that the energy of the emitted electrons depends not on the intensity of the light, but only on its color, or more precisely, on its frequency or wavelength. Based on the previous theory of radiation, this could not be explained. However, Einstein explained these observations by relying on Planck's hypothesis, which he interpreted by assuming that light consists of so-called light quanta, or quanta of energy, that move through space like tiny particles. According to Planck's hypothesis, the energy of an individual light quantum must equal the frequency of light multiplied by Planck's constant. The other problem was the specific heat capacity of solid bodies. The existing theory of specific heat capacity led to values that agreed well with experiments in the high temperature range, but were much higher than observed values at low temperatures. Einstein was again able to show that such behavior of solids could be understood through Planck's quantum hypothesis, applying it to the elastic vibrations of atoms in a solid. These two results were a significant step forward in the further development of the new theory, as they revealed Planck's constant of action in various fields not directly related to the problem of thermal radiation. These results also revealed the deeply revolutionary nature of the new hypothesis, as Einstein's interpretation of quantum theory led to an explanation of the nature of light that was completely different from the conventional understanding. Over time, explanations based on wave representation became less relevant. Consequently, light can be defined either as the propagation of electromagnetic waves, a fact accepted based on Maxwell's work and Hertz's experiments, or as something composed of individual light quanta, or energy packets that move through space at high speed. But can light be both? Einstein certainly knew that known experiments on diffraction and interference could only be explained based on wave representations. He also could not dispute the existence of a complete contradiction between his hypothesis of light quanta and wave representations. Einstein did not even attempt to eliminate the internal contradictions of his interpretation. He accepted the contradictions as something that could probably be understood much later. Meanwhile, the experiments of Becquerel, Curie, and Rutherford provided a bit more clarity regarding the structure of the atom. In 1911, Rutherford, based on observations of beta rays passing through matter, proposed his famous model of the atom, consisting of a positively charged atomic nucleus containing almost all the mass of the atom, and electrons that move around the nucleus, much like planets orbiting the sun. The chemical bond between atoms of different elements is explained by the interaction between the outer electrons of neighboring atoms. The chemical bond is not directly related to the nucleus. The atomic nucleus determines the chemical properties of the atom only indirectly through its electric charge, as the latter determines the number of electrons in a neutral atom. This model, however, could not explain one of the most characteristic features of the atom, namely its remarkable stability. No planetary system governed by Newton's laws of mechanics could ever return to its original state after colliding with another similar system, whereas, for example, a carbon atom remains a carbon atom even after colliding with other atoms, or after interacting with other atoms to form a chemical compound. The explanation for this unusual stability was provided in 1913 by Niels Bohr through the application of Planck's quantum hypothesis to Rutherford's atomic model. If an atom can change its energy only discontinuously, this must mean that the atom exists only in discrete stationary states, the lowest of which is the normal state of the atom. Therefore, after any interaction, the atom ultimately always returns to this normal state. By applying quantum theory to the atomic model, Bohr was able not only to explain the stability of the atom, but also, in some simple cases, to provide a theoretical explanation for the linear spectra produced when atoms are excited by electric charge or heat. His theory, in describing the motion of electrons, was based on a combination of classical mechanics and quantum conditions imposed on classical laws of motion to isolate discrete stationary states among other states. Later, Sommerfeld provided an exact mathematical formulation of these conditions. It was clear to Bohr that quantum conditions, in a certain sense, undermine the internal consistency of Newtonian mechanics. In the simplest case of the hydrogen atom, based on Bohr's theory, one can calculate the frequency of emitted light, and the agreement between theoretical calculations and observations was complete. In reality, these frequencies differed from the orbital frequencies of electrons and the higher harmonics of these frequencies, and this circumstance immediately indicated that the theory was still full of contradictions. Despite this, it likely contained a substantial degree of truth. It qualitatively explained the chemical properties of atoms and their linear spectra. The existence of discrete stationary states was directly confirmed by experiments conducted by Frank and Hertz, Stern, and Gerlach. Thus, Bohr's theory opened a new area of research. A large amount of experimental material obtained through spectroscopy over several decades became a source of information for the same purpose when studying the quantum laws of electron motion. Many experiments conducted by chemists could be utilized. Dealing with this experimental material, physicists gradually learned to ask the right questions. Often, a well-posed question signifies more than half the solution to a problem. What are these questions? Practically all of them dealt with the explicit and astonishing contradictions in the results of various experiments. How can it be that the same radiation, which produces an interference pattern and thus proves the existence of the underlying wave motion, simultaneously produces the photoelectric effect and must therefore consist of moving light quanta? How can it be that the frequency of the orbital motion of electrons in an atom is not also the frequency of the emitted radiation? Does this not imply that there is no orbital motion at all? But if the concept of orbital motion is incorrect, then what happens to the electron inside the atom? One can see the electrons moving in a Wilson chamber. Some of them were previously part of the atom and were ejected from it. Why then do they not move inside the atom? Similarly, one might imagine that in the normal state, atoms and electrons are at rest. But there are states with higher energies in which electrons possess angular momentum, and therefore, in these states, a state of rest for the electrons is absolutely excluded. Many such examples could be listed. It became clear to everyone that attempting to describe atomic processes in terms of ordinary physics leads to contradictions. By the early 20s, physicists gradually became accustomed to these difficulties. They developed a sort of intuition, albeit not very clear, regarding where difficulties would likely arise, and they learned to avoid these difficulties. Finally, they learned which description of atomic processes in a given experiment would lead to the correct result. This knowledge was not sufficient to provide a comprehensive and consistent picture of quantum processes, but it significantly changed physicists' thinking, allowing them to embrace the spirit of quantum theory even before a rigorous formulation of quantum theory was provided. They knew more or less accurately what the result of a given experiment would be. They often discussed so-called thought experiments. Such experiments were devised to clarify some particularly important question, regardless of whether the actual experiment could be conducted or not. Of course, it was important that the experiment could, in principle, be carried out. The experimental technique could be of any complexity. These thought experiments proved extremely useful in clarifying certain problems, where it was impossible to reach consensus among physicists regarding the likely outcome of such an experiment. Often, it was possible to devise a similar but simpler experiment that could actually be performed. The experimental results significantly contributed to the clarification of quantum theory. A remarkable event of those years was the fact that as this clarification progressed, the paradoxes of quantum theory did not disappear. Rather, they emerged in increasingly explicit forms and became sharper. For example, at that time, Compton conducted an experiment on the scattering of X-rays. Based on previous experiments on the interference of scattered light, it was entirely evident that scattering primarily occurs as follows. An incoming light wave ejects an electron oscillating at the same frequency. Then the oscillating electron emits a spherical wave at the frequency of the incoming wave, thereby causing the scattered light. However, in 1923, Compton discovered that the frequency of the scattered X-rays differed from that of the incoming rays. This change in frequency can be explained by assuming that scattering represents a collision of a quantum of light with an electron. Upon impact, the energy of the light quantum changes, and since the product of frequency and Planck's constant equals the energy of the light quantum, the frequency must also change. But how can one explain light waves in this case? The two experiments, one on the interference of scattered light and the other on the change in the frequency of scattered light, contradict each other so fundamentally that seemingly no solution could be found. At that time, many physicists were already convinced that these apparent contradictions belonged to the internal nature of atomic physics. Therefore, de Broglie, in France, in 1924, attempted to extend the dualism of wave and particle descriptions to elementary particles of matter, particularly electrons. He showed that the motion of electrons could correspond to some wave of matter, just as the motion of a light quantum corresponds to a light wave. Of course, at that time, it was not clear what the word correspond meant in this context. De Broglie proposed to explain the conditions of Bohr's quantum theory using concepts of matter waves. A wave moving around the atomic nucleus, for geometric reasons, can only be a stationary wave. The length of the orbit must be a multiple of the wavelength. Thus, de Broglie proposed to bridge the gap between the concepts of conditions that remained foreign to the mechanics of electrons and the dualism of waves and particles. Consequently, in Bohr's theory, the differences between the calculated orbital frequency of the electron and the frequency of radiation indicated the limitations of the concept of electron orbit. After all, from the very beginning, this concept raised significant doubts. On the other hand, in the case of highly excited states, where electrons move far from the nucleus, one must agree that electrons move just as they do when observed in a Wilson chamber. Therefore, in this case, the term electron orbit could be used. For this reason, it seems quite satisfactory that for highly excited states, the frequency of radiation approaches the orbital frequency, more precisely, the orbital frequency and the higher harmonic components of that frequency. Bohr, in one of his early works, asserted that the intensity of spectral lines of radiation should approximately agree with the intensity of the corresponding harmonic components. This so-called correspondence principle proved very useful for approximating the calculation of the intensity of spectral lines. Thus, it created the impression that Bohr's theory provided a qualitative and quantitative picture of what occurs inside the atom, and that, at least, some new features in the behavior of matter could be qualitatively expressed using quantum conditions, which, in turn, were somehow related to the dualism of wave and particle. The precise mathematical formulation of quantum theory ultimately emerged through the development of two different directions. One direction was associated with Bohr's correspondence principle. In this direction, it was necessary to abandon the concept of electron orbit and use it only approximately in the limit of large quantum numbers, that is, large orbits. In this last case, the frequency and intensity of radiation correspond to the electron orbit. Radiation corresponds to what mathematicians call the Fourier representation of the electron's orbit. Thus, it is quite logical to think that mechanical laws should be recorded not as equations for the coordinates and velocities of electrons, but as equations for the frequency and amplitudes of their Fourier decomposition. Based on such ideas, it became possible to transition to mathematically representable relationships for quantities that correspond to the frequency and intensity of radiation. This program could indeed be realized in the summer of 1925. It led to a mathematical formalism that was called matrix mechanics, or, more generally, quantum mechanics. The equations of motion of Newtonian mechanics were replaced by similar equations for linear algebraic forms, which in mathematics are called matrices. It is quite remarkable that many of the old results of Newtonian mechanics, such as the conservation of energy, remained valid in the new formalism. Later investigations by Bohr, Jordan, and Dirac showed that the matrices representing the coordinates and momentum of the electron do not commute with each other. In mathematical terms, this fact indicated the most significant and essential differences between quantum mechanics and classical mechanics. The other direction stemmed from de Broglie's ideas about matter waves. Schrödinger attempted to write a wave equation for the stationary de Broglie waves surrounding the atomic nucleus. In early 1926, he succeeded in deriving the energy values for the stationary states of the hydrogen atom as the eigenvalues of his wave equation, and he was able to provide general rules for transforming classical equations into corresponding wave equations, which, however, pertain to some abstract mathematical space, namely, a multidimensional configuration space. Later, he showed that his wave mechanics is mathematically equivalent to the earlier formalism of quantum or matrix mechanics. Thus, we finally obtained a consistent mathematical formalism that can be expressed in two equally valid ways, either through matrix relationships or through wave equations. This mathematical formalism provided correct energy values for the hydrogen atom. It took less than a year to discover that correct results were also obtained for the helium atom and, in more complex cases, for heavy atoms. However, in what sense does the new formalism describe atomic phenomena? After all, the paradoxes of the particle and wave picture had not yet been resolved, nor were they merely contained in a hidden form within the mathematical scheme. In the direction of genuinely understanding quantum theory, the first and very interesting step was already made in 1924 by Bohr, Kramer, and Slater. They attempted to eliminate the apparent contradiction between the wave and particle pictures by introducing the concept of a wave of probability. Electromagnetic light waves were interpreted not as real waves, but as waves of probability, the intensity of which at each point determines the likelihood that a quantum of light may be emitted or absorbed by an atom at that location. This representation led to the conclusion that apparently the laws of conservation of energy and dynamic variables might not hold in every individual case, and thus we are dealing with statistical laws, so that energy is conserved only in a statistical average. In reality, this conclusion was incorrect, and the relationship between the wave and particle pictures of radiation later proved to be even more complex. However, the work of Bohr, Kramer, and Slater contained a significant feature of the correct interpretation of quantum theory. With the introduction of the wave of probability into theoretical physics, a completely new concept was introduced in mathematics or statistical mechanics. The wave of probability signifies a judgment about the degree of our knowledge of the actual situation. When rolling a die, we cannot trace the details of the hand's motion that determine the outcome of the roll, and therefore we say that the probability of rolling a specific number is 1 in 6, since the die has 6 faces. However, the wave of probability, according to Bohr, Kramer, and Slater, was something much more. It represented something akin to the striving for a certain course of events. It signified a quantitative expression of the old concept of potentiality in Aristotelian philosophy. It introduced a strange kind of physical reality that lies approximately between possibility and actuality. Later, when the mathematical formulation of quantum theory was completed, Bohr utilized this idea of the wave of probability within the framework of the formalism, providing a clear definition of a mathematical quantity that could be interpreted as a wave of probability. The wave of probability was not a three-dimensional wave like radio waves or elastic waves, but a wave in multidimensional configuration space, an abstract mathematical quantity. It became known through Schrödinger's research. Even at that time, in the summer of 1926, it was still not clear in every case how to use the mathematical formalism to describe a given experimental situation. It was true that they already knew how to describe stationary states, but it was not yet known how to explain much simpler phenomena, such as the motion of electrons in a Wilson chamber. When, in the summer of 1926, Schrödinger demonstrated that in the formalism of his wave mechanics, the mathematical validity of quantum mechanics, he temporarily abandoned the notion of quanta and quantum leaps and attempted to replace electrons in the atom with three-dimensional waves of matter. The impetus for this attempt was that, according to his theory, the energy levels of the hydrogen atom are the eigenfrequencies of certain stationary waves. Therefore, Schrödinger believed it would be a mistake to consider them as energy values that are not frequencies, but rather not energies at all. However, during a discussion that took place in Copenhagen in the autumn of 1926 between Bohr, Schrödinger, and the Copenhagen group of physicists, it became evident that such an interpretation was insufficient even to explain Planck's law of thermal radiation. In the months following this discussion, intensive study in Copenhagen of all questions related to the interpretation of quantum theory ultimately led to a completed and, as many physicists believe, satisfactory explanation of the entire situation. However, it was not an explanation that could be easily accepted. Could nature really be as absurd as it appears to us in these atomic experiments? The final resolution came from two directions. One path involved reformulating the question. Instead of asking how a given experimental situation can be described using the known mathematical scheme, a different question is posed. Is it true that in nature only such an experimental situation exists that can be expressed in the mathematical formalism of quantum theory? The assumption that this is the correct formulation of the question led to a limitation of the application of concepts that, since Newton's time, have formed the foundations of classical physics. It is true that one could speak, as in Newtonian mechanics, of the coordinates and velocities of electrons. These quantities can be observed and measured, but one cannot measure both quantities simultaneously with any precision. It turned out that the product of these two uncertainties cannot be less than Planck's constant divided by the mass of the particle in question. Similar relationships can be formulated for other experimental situations. They are called uncertainty relations, or the principle of uncertainty. Thus, it was established that the old concepts do not entirely satisfy nature. The other path was related to Bohr's concept of complementarity. Schrödinger described the atom as a system that consists not of a nucleus and electrons, but of an atomic nucleus and material waves. Undoubtedly, this picture of matter waves also contains a degree of truth. Bohr viewed both pictures, particle and wave, as two complementary descriptions of the same reality. Each of these descriptions can only be partially correct. One must specify the limits of applicability of the particle picture, just as one must specify the limits of applicability of the wave picture. Otherwise, contradictions cannot be avoided. But if one takes into account the limits imposed by the uncertainty relations, then the contradictions disappear. Thus, by the beginning of 1927, a consistent interpretation of quantum theory was finally reached, often referred to as the Copenhagen Interpretation. This interpretation withstood scrutiny at the Solvay Congress in Brussels in the autumn of 1927. The experiments that led to frustrating paradoxes were once again discussed in detail, especially by Einstein. New thought experiments were devised to uncover the remaining internal contradictions of the theory. However, the theory proved free from them, and apparently satisfied all the experiments known at that time. It may be worth noting that it took more than a quarter of a century to progress from Planck's hypothesis of the existence of the quantum of action to a genuine understanding of the laws of quantum theory. From this, it is clear how great the changes in our fundamental concepts of reality must be in order to fully comprehend the new situation. The Copenhagen interpretation of quantum theory begins with a paradox. Every physical experiment, whether it pertains to everyday phenomena or atomic physics, must be described in the terms of classical physics. The concepts of classical physics form the language through which we describe our experiences and results. We cannot replace these concepts with anything else, and their applicability is limited by the uncertainty relations. We must keep in mind the limited applicability of classical concepts and not attempt to go beyond this limitation. To better understand this paradox, it is necessary to compare the interpretation of an experiment in classical and quantum physics. For example, in Newtonian celestial mechanics, we start by defining the position and velocity of a planet, the motion we intend to study. The results of observation are translated into mathematical language by deriving the values of the coordinates and momentum of the planet from the observations. Then, using these numerical values of coordinates and momentum for a given moment in time, one obtains the values of coordinates or other properties of the system for subsequent moments in time from the equations of motion. In this way, the astronomer predicts the motion of the system. For instance, he can predict the exact time of a solar eclipse. In quantum theory, everything occurs differently. Suppose we are interested in the motion of an electron in a Wilson chamber, and we have determined the coordinates and velocity of the electron through some observation. However, this determination cannot be precise. It contains, at the very least, uncertainties due to the uncertainty relations, and likely, in addition, will contain even more uncertainties related to the difficulties of the experiment. The first group of uncertainties allows us to translate the result of the observation into the mathematical scheme of quantum theory. The probability function, which describes the experimental situation at the moment of measurement, is recorded with consideration for the possible measurement uncertainties. This probability function represents a combination of two different elements. On one hand, the fact, and on the other hand, the degree of our knowledge of that fact. This function characterizes factual reliability, as it assigns a probability of 1 to the initial situation. It is certain that the electron is moving at the observed speed in the observed point. Here, observed means within the limits of the experiment's accuracy. This function characterizes the degree of accuracy of our knowledge, as another observer might determine the position of the electron even more precisely. At least to some extent, experimental error or uncertainty is regarded not as a property of electrons, but as a deficiency in our knowledge of the electron. This deficiency of knowledge is also expressed through the probability function. In classical physics, during precise investigations, observational errors are also taken into account. As a result, one obtains a probability distribution for the initial values of coordinates and velocities, which bears some resemblance to the probability function of quantum mechanics. However, the specific uncertainty due to the uncertainty relations is absent in classical physics. If, in quantum theory, the probability function for the initial moment has been defined from the given observations, then one can calculate, based on the laws of this theory, the probability function for any subsequent moment in time. Thus, it is possible to determine in advance the probability that a quantity will have a specific value upon measurement. For example, one can specify the probability that at a certain subsequent moment in time, the electron will be found at a specific point in the Wilson chamber. It should be emphasized that the probability function does not describe the actual course of events over time. It characterizes the tendency of an event, the possibility of an event, or our knowledge of an event. The probability function is connected to reality only under one essential condition. To reveal a specific property of the system, new observations or measurements must be made. Only in this case does the probability function allow for the calculation of the likely outcome of a new measurement. In this context, the measurement result is again provided. In the concepts of classical physics, the theoretical interpretation involves three distinct stages. First, the initial experimental situation is translated into a probability function. Second, the change of this function over time is established. Third, a new measurement is made, the expected result of which is then determined from the probability function. A necessary condition for the first stage is the fulfillment of the uncertainty relation. The second stage cannot be described in the terms of classical physics. It is impossible to specify what happens to the system between the initial measurement and the subsequent ones. Only the third stage allows us to transition from the possible to the actual. We will clarify these three stages using a simple thought experiment. It has already been noted that an atom consists of a nucleus and electrons that move around the nucleus. It has also been established that the concept of an electron orbit is in some sense questionable. However, regarding this last assertion, it can be said that, at least in principle, one can observe an electron in its orbit. Perhaps we would see the electron moving along its orbit if we could observe it using a microscope with high resolving power. However, such resolving power cannot be achieved with a microscope using ordinary light, as only a microscope utilizing gamma rays with a wavelength smaller than the size of an atom would be suitable for this purpose. Is it possible to translate the results of the observation into a probability function at the first stage? This is possible if the uncertainty relation holds after the experiment. The position of the electron is known with precision, determined by the wavelength of the gamma rays. Let us assume that before the observation, the electron is essentially at rest. During the observation, at least one quantum of gamma radiation will inevitably pass through the microscope and, as a result of its collision with the electron, change its direction of motion. Therefore, the electron will also experience the impact of the quantum, altering its momentum and speed. It can be said that the uncertainty of this change is such that the uncertainty relation holds true. After the collision, this is guaranteed. Thus, the first step presents no difficulties. At the same time, it can be easily shown that the motion of electrons around the nucleus cannot be observed. The second stage, the quantitative calculation of the probability function, shows that the wave packet does not move around the nucleus, but away from it, as even the first light quantum knocks out the electron. The momentum of the gamma quanta is significantly greater than the initial momentum of the electron, provided that the wavelength of the gamma rays is much smaller than the size of the atom. Therefore, just one light quantum is sufficient to knock out the electron, and consequently, one can never observe more than one point on the electron's trajectory. Thus, the assertion that there is no trajectory of the electron in the usual sense is not contradicted by experience. The next observation of the third stage detects the electron as it exits the atom. It is impossible to visually describe what happens between two consecutive observations. Of course, one might say that the electron must be somewhere between the two observations, and that, apparently, it describes some semblance of a trajectory, even if it is impossible to establish this trajectory. Such reasoning makes sense from the perspective of classical physics. In quantum theory, such reasoning represents an unjustified abuse of language. At present, we can leave open the question of whether this assumption pertains to the form of statements about atomic processes or to the processes themselves, that is, whether it relates to epistemology or ontology. In any case, when formulating statements regarding the behavior of atomic particles, we must be extremely cautious. In fact, we cannot speak of particles at all. It is often more appropriate in many experiments to speak of matter waves. For example, a standing wave around the nucleus. Such a description will, of course, contradict another description if we do not take into account the limits established by the uncertainty relation. This limitation eliminates contradictions. The application of the concept of matter waves is appropriate when discussing the radiation of atoms. Radiation, possessing a certain frequency and intensity, provides us with information about the changing distribution of charges in the atom. In this context, the wave picture is closer to a brush than to a corpuscular one. Therefore, Bohr advised using both pictures, which he termed complementary. Both pictures, of course, exclude each other, as a specific object cannot be both a particle, that is, a substance confined to a small volume, and a wave, that is, a field spreading over a large volume at the same time. But both pictures complement each other. If one uses both pictures, transitioning from one to the other and back, one ultimately arrives at a correct representation of the remarkable form of reality that lies behind our experiments with atoms. Bohr applies the concept of complementarity in different aspects when interpreting quantum theory. Knowledge of a particle's position includes additional knowledge about its speed or momentum. If we know a certain quantity with great precision, we cannot determine another complementary quantity with the same precision without losing the accuracy of the first knowledge. However, to describe the behavior of a system, we need to know both quantities. The space-time description of atomic processes, in addition to the given or deterministic description, similar to the coordinate function in Newtonian mechanics, the probability function satisfies the equation of motion and change over time, is fully determined by quantum mechanical equations, but it does not provide any space-time description of the system. On the other hand, observation requires a space-time description. Every observation, by changing our knowledge of the system, alters the theoretically calculated behavior of the probability function. Generally, the dualism between two different descriptions of the same reality is no longer viewed as a fundamental difficulty, as the mathematical formulation of the theory indicates that the theory contains no contradictions. The dualism of both complementary pictures is vividly manifested in the flexibility of the mathematical formalism. Usually, this formalism is written in such a way that it resembles Newtonian mechanics with its equations of motion for the coordinates and speeds of particles. Through simple transformation, this formalism can be represented as a wave equation for three-dimensional matter waves, but these waves have the character of complex quantities, fields, matrices, or operators. This explains that the ability to use various complementary pictures has its analogy in different transformations of the mathematical formalism. In the Copenhagen Interpretation, This is not associated with any difficulties. Difficulties in understanding the Copenhagen interpretation always arise when one poses the well-known question: what actually happens in an atomic process? First of all, as mentioned above, measurement and the result of observation are always described in the terms of classical physics. What is derived from the observation is the probability function. It represents a mathematical expression of the union of statements about possibility and tendency with statements about our knowledge of the fact. Therefore, we cannot fully determine the result of the observation. We are unable to say what happens in the interval between this observation and the next. At first glance, this appears to imply that we have introduced a subjective element into the theory. Thus, we say that what occurs depends on how we observe it, or at least depends on the very fact that we are observing it. Before addressing this objection, it is essential to clarify precisely why such difficulties arise when attempting to describe what happens between two consecutive observations. It is appropriate in this context to discuss the following thought experiment. Let us assume that a point source of monochromatic light emits light onto a black screen with two small holes. The diameter of the holes is comparable to the wavelength of the light, while the distance between the holes significantly exceeds the wavelength of the light. At some distance behind the screen, the passing light falls on a photographic plate. If this experiment is described in terms of the wave picture, one can say that the primary wave passes through both holes, thus creating two secondary spherical waves that originate from the holes and interfere with each other. The interference leaves bands of strong and weak intensity on the photographic plate, known as interference fringes. The darkening on the plate is a chemical process caused by individual light quanta. Therefore, it is also important to describe the experiment from the perspective of the light quantum representation. If one could discuss what happens to an individual light quantum in the interval between its emission from the source and its arrival at the photographic plate, one might reason as follows. An individual light quantum can pass through either the first or the second hole. If it passes through the first hole, the probability of its hitting a specific point on the photographic plate does not depend on whether the second hole is open or closed. The probability distribution on the plate would be as if only the first hole were open. If the experiment is repeated many times, covering all cases in which the light quantum passed through the first hole, the darkening on the plate should correspond to this probability distribution. If we only consider those light quanta that pass through the second hole, the darkening will correspond to the probability distribution derived from the assumption that only the second hole is open. Therefore, the total darkening should be the exact sum of both darkenings. In other words, there should be no interference pattern. But we know that the experiment produces an interference pattern. Thus, the assertion that the light quantum passes through either the first or the second hole is questionable and leads to contradiction. This example illustrates that the concept of a probability function does not provide a space-time description of the event occurring in the interval between two observations. Every attempt to find such a description leads to contradiction. This means that the very concept of an event must be limited to observation. This conclusion is quite significant, as it seems to show that observation plays a decisive role in atomic events, and that reality differs depending on whether we observe it or not. To clarify this assertion, let us analyze the process of observation. It is worth recalling that in natural science, we are not interested in the universe as a whole, including ourselves, but only in a certain part of it, which we make the object of our study. In atomic physics, this aspect typically represents an extremely small object, namely atomic particles, or groups of such particles. But it is not merely a matter of size. What is essential is that a large part of the universe, including ourselves, does not belong to the subject of observation. The theoretical interpretation of the experiment begins at the level of both stages already mentioned. At the first stage, a description of the experiment is made in terms of classical physics. This description ultimately connects at this stage with the first observation, and then the description is formulated using the probability function. The probability function, in turn, adheres to the laws of quantum mechanics, and its change over time is continuous and calculated based on initial conditions. This is the second stage. The probability function unites objective and subjective elements. It contains a statement about probability, or, better yet, about tendency, potential in Aristotelian philosophy, and these statements are entirely objective. They do not depend on any observation. In addition, the probability function contains a statement regarding our knowledge of the system, which is subjective, as it can differ for various observers. In favorable cases, the subjective element of the probability function becomes negligible compared to the objective element. In such cases, one speaks of a pure case. When addressing the next observation, the result of which is predicted by theory, it is essential to determine whether the subject was interacting with the rest of the world before, or, at least, at the moment of observation, for example, with the experimental setup, measuring instruments, and so on. This means that the equation of motion for the probability function contains the influence of the interaction exerted on the system by the measuring instrument. This influence introduces a new element of uncertainty, since the measuring instrument is described in terms of classical physics. Such a description contains all inaccuracies regarding the microscopic structure of the instrument, as known from thermodynamics. Furthermore, since the instrument is connected to the rest of the world, the description effectively contains inaccuracies regarding the microscopic structure of the entire world. These inaccuracies can be considered objective, as they are a simple consequence of the fact that the experiment is described in terms of classical physics, and since they do not depend in detail on the observer, they can be considered subjective, as they indicate our incomplete knowledge of the world. After the interaction has occurred, even in the case of a pure case, the probability function will contain an objective element of tendency or possibility and a subjective element of incomplete knowledge. For this reason, the result of the observation as a whole cannot be predicted precisely. Only the probability of a certain observation result can be predicted, and this probability statement can be verified through repeated experimentation. The probability function, unlike mathematical schemes and Newtonian mechanics, describes not a specific event, but at least in the process of observation, the entire ensemble, the collection of possible events. Self-observation dramatically alters the probability function. It selects from all possible events the one that actually occurred. Since our knowledge changes discontinuously under the influence of observations, the quantities involved in its mathematical representation also change discontinuously, and thus we speak of a quantum leap. If someone attempts to critique quantum theory based on the old saying, nature does not make leaps, it can be responded that our knowledge undoubtedly changes discontinuously. It is this fact of the discontinuous change in our knowledge that justifies the use of the term quantum leap. Consequently, the transition from possibility to reality occurs in the process of observations. If we describe what happens in some atomic event, we must start from the understanding that the word happens refers only to the observation itself. In this situation, it signifies not a psychological, but a physical process of observation. And we are entitled to say that the transition from possibility to reality has occurred as soon as the object interacts with the measuring instrument and the rest of the world. This transition is not related to the registration of the observation result in the observer's consciousness. However, the discontinuous change in the probability function occurs due to the act of registration. As in this case, the question concerns the discontinuous change in our knowledge. To what extent have we ultimately arrived at an objective description of the world, and especially atomic phenomena? Classical physics was based on the assumption, or one might say, the illusion, that one can describe the world, or at least a part of it, without referring to oneself. To a significant extent, this was possible. For example, we know that the city of London exists independently of whether we see it or not. One could say that classical physics provides precisely the idealization of the world, through which one can speak of the world or its part while disregarding oneself. Its success has led to a universal ideal of objective description of the world. For a long time, objectivity has been the criterion of the value of scientific discoveries. Does the Copenhagen interpretation of quantum theory correspond to this ideal? Probably, we can say that, as far as possible, quantum theory aligns with this ideal. Certainly, quantum theory contains no truly subjective features, and it does not consider the mind or consciousness of the physicist as part of the atomic event. But it begins with the division of the world into objects and the rest of the world, with the condition that this rest of the world is described in terms of classical physics. The very division is to some extent arbitrary, but historically it is a direct consequence of the scientific method of past centuries. The application of classical concepts is the result of the overall spiritual development of humanity. In a certain sense, this touches upon ourselves, and thus our description cannot be deemed entirely objective. It was mentioned earlier that the Copenhagen interpretation of quantum theory begins with a paradox. It starts from the position that we must describe experiments in terms of classical physics, while also acknowledging that these concepts do not accurately correspond to nature. The contradiction between these initial positions accounts for the statistical nature of quantum theory. Because of this, some have suggested completely abandoning classical concepts, hoping that a radical change in the concepts describing the experiment would lead to a non-statistical, fully objective description of nature. However, these considerations are based on a misunderstanding of the concept of classical physics, which is a refined understanding of our everyday life and forms a crucial part of the language that underpins all natural science. Our actual position in natural science is such that to describe an experiment, we effectively use or must use classical concepts. Otherwise, we would not understand each other. The task of quantum theory is precisely to explain the experiment on this basis. There is no point in interpreting what could be undertaken if we were of a different nature than what we actually are. In this regard, we must clearly understand, in the words of Descartes, that nature existed before humanity, but humanity existed before natural science. The first half of this statement justifies classical physics with its ideals of complete objectivity, while the second half explains why we cannot escape the paradoxes of quantum theory and the necessity of applying classical concepts. At this point, a few remarks should be made regarding the actual method of quantum theoretical interpretation of atomic events. It was previously noted that we always face the necessity of dividing the world into objects subject to study and the rest of the world, including ourselves. This division is to some extent arbitrary. However, it should not lead to differences in the final results. For example, let us combine the measuring instrument or its part with the object and apply the law of quantum theory to this more complex object. It can be shown that such a modification of the theoretical approach does not actually change the predictions about the outcome of the experiment. This mathematically follows from the fact that the laws of quantum theory for phenomena in which Planck's constant is considered a very small quantity are almost identical to classical laws. However, it would be a mistake to assume that such an application of the laws of quantum theory can exclude fundamental paradoxes. A measuring instrument only justifies its purpose when it is closely connected with the rest of the world, when there is a physical interaction between the measuring instrument and the observer. Therefore, inaccuracies regarding the microscopic behavior of the world, just like in the case of the first interpretation, penetrate into the quantum mechanical description of the world. If the measuring instrument were isolated from the rest of the world, it could not be described in terms of classical physics. In this regard, Bohr argued that it would probably be more accurate to say otherwise, namely, that the division of the world into objects and the rest of the world is arbitrary. When investigating atomic processes, our goal is to understand specific phenomena and determine how they follow from general laws. Therefore, the part of matter and radiation that participates in its lines represents a natural subject for theoretical interpretation and must be separated from the instrument used. Thus, in the description of atomic processes, a subjective element is once again introduced as the measuring instrument is created by the observer. We must remember that what we observe is not nature itself, but nature as it appears in the form revealed by our way of posing questions. The scientific work of a physicist consists of posing questions about nature in the language we use and attempting to obtain answers through experiments conducted with the means at our disposal. In this context, Bohr's words about quantum theory come to mind. If one seeks harmony in life, one must never forget that in the game of life, we are simultaneously both spectators and participants. It is clear that in scientific terms, our own activity becomes significant in nature, where it is necessary to deal with areas of nature that can only be penetrated through the most complex technical means. The concept of the atom is much older than modern natural science. It has its roots in ancient natural philosophy, being a central concept of the materialism of Leucippus and Democritus. On the other hand, the modern understanding of atomic phenomena bears very little resemblance to the understanding of the atom in earlier materialistic philosophy. Moreover, one could say that modern atomic physics has pushed natural science off the materialistic path it stood on in the 19th century. Therefore, it would be interesting to compare the formation of the concept of the atom in Greek philosophy with its understanding in modern science. The idea of the existence of the smallest indivisible particles of matter arose in close connection with the development of concepts of matter, being, and becoming, characterizing the first period of Greek philosophy. This period began in the 6th century BCE with Thales, the founder of the Milesian school, who, according to Aristotle, believed that water is the material basis of all things. No matter how strange this statement may seem, it expresses three fundamental philosophical ideas, as Nietzsche emphasized. First, this statement contains a question about the material foundation of all things. Second, it contains a demand for a rational answer to this question without reference to myths and mystical ideas. Third, it contains the assumption of the possibility of understanding the world based on a single fundamental principle. Thales' statement was the first expression of the idea of a fundamental substance, of a primary element from which all things are formed. In this context, the word substance does not yet have the clear materialistic meaning currently attributed to it. This concept of substance also included the idea of life. According to Aristotle, Plato also asserted that all things are full of gods. All of this relates to the material foundation of things. It is not difficult to imagine that Thales arrived at his views primarily through meteorological observations. It is evident that among the multitude of things, water can take on the most diverse forms and exist in the most varied states. In winter, it becomes ice and snow. It can turn into vapor, from which clouds are formed. It transforms into land, where a river forms its delta, and it can emerge from the ground as a spring. Water is the condition for all life. Therefore, in general, if there is anything resembling a fundamental element, it is natural to consider water as the primary element. The idea of matter as the fundamental substance was developed by Anaximander, a student of Thales. Anaximander denied that the primary matter could be ordinary water or any other known substance. He taught that the first matter is infinite, eternally unchanging, and fills the entire world. This first matter transforms into various substances known to us. According to Theophrastus, Anaximander believed that from which things arise, they must also return according to justice, for they must bear punishment for injustice at the appointed time. In this philosophy, the antithesis of being and becoming plays a decisive role. The first matter, unchanging, infinite, undifferentiated being, takes on various forms in the process of becoming, which are in continuous, eternal struggle. The process of becoming is viewed as a limitation, a reduction of infinite being, as destruction in struggle, as a curse that is ultimately redeemed by returning to non-material being. The uncertainty and struggle referred to are the oppositions between hot and cold, between fire and water, between wet and dry, and so forth. The temporary victory of one over the other is an injustice that leads to redemption at the appointed time. According to Anaximander, there exists an eternal movement, a continuous creation and destruction of worlds from the infinite to the infinite. For comparison, the ancient philosophy with our modern problems is perhaps interesting in that contemporary atomic physics raises anew the question, is the primary matter one of the known substances, or is it something that transcends them? Currently, attempts are being made to find a fundamental law of motion of matter from which all elementary particles with their properties can be mathematically derived. This fundamental equation of motion may refer either to waves of a known type, such as proton or meson waves, or to waves of a fundamentally different kind, having nothing in common with the waves of known elementary particles. In the first case, it would mean that the multitude of elementary particles could be explained using a few fundamental, so-called elementary particles. In fact, in the last 2 decades, theoretical physics has mainly followed this possibility. In the second case, all the diversity of elementary particles is explained by some universal matter, which can be called energy or matter. In this case, none of the elementary particles is fundamentally distinguished from the others as a fundamental particle. This last viewpoint corresponds to Anaximander's doctrine, and I am convinced that this perspective is correct in modern physics. However, let us return once again to Greek philosophy. The Milesian philosopher Anaximenes, probably a student of Anaximander, taught that the primary matter from which everything consists is air. He believed that just as our soul is nothing other than air, which unites us, so the breath of air unites the entire world. Anaximenes introduced into Milesian philosophy the idea that the cause of the transformation of primary matter into other substances is the process of condensation and rarefaction. At that time, the transformation of water vapor into clouds was, of course, known, while the distinction between water vapor and clouds had not yet been understood. The philosophy of Heraclitus. The concept of becoming took the first place. Heraclitus considered the primary matter to be moving fire. The difficulty of connecting the idea of a single principle with the existence of infinite transformations of phenomena was resolved by Heraclitus through the assumption that the continuous struggle between opposites is a kind of harmony. For Heraclitus, the world is simultaneously one and many. It is precisely the tension of opposites that forms the unity of the whole. He asserted that struggle is the universal beginning of all being, and this struggle is simultaneously a balancing act. Things arise and disappear again in the process of struggle. If one surveys Greek philosophy from its inception to the moment when the philosophy of Heraclitus emerged, it is easy to see that from the very beginning it bore within itself the opposition of the concepts of the one and the many. In our understanding, the world unfolds as an infinite diversity of things and events, colors, and sounds. But to comprehend it, it is necessary to establish a certain order. Order means clarifying what is identical. It signifies unity. Based on this, the conviction arises that there must exist a single principle. Yet at the same time, a difficulty arises. How does the infinite diversity of things flow from it? The natural starting point is that there exists a material first cause of things, since the world consists of matter. However, when logically carried to its conclusion, the idea of unity fundamentally leads to an infinite, unchanging, non-substantial being, which cannot itself explain the infinite diversity of things, regardless of whether we consider this being material or not. From here arises the polarity of being and becoming, and ultimately Heraclitus's idea that the fundamental principle is change, eternal transformation, which, in the words of the poet, renews the world. But transformation itself is not a material cause. This explains why, in Heraclitus's philosophy, the material cause is represented in the form of fire. Fire as the first element is simultaneously both matter and the driving force. We can now say that modern physics, in a certain sense, closely follows the teachings of Heraclitus. If we replace the word fire with the word energy, then almost exactly the statements of Heraclitus can be considered statements of modern science. In fact, energy is what all elementary particles, all atoms, and thus all things are made of. At the same time, energy is the driving force. Energy is a substance. Its total amount does not change. And, as can be seen in many atomic experiments, elementary particles are created from this substance. Energy can transform into motion, heat, light, or electric tension. Energy can be considered the primary cause of all changes in the world. However, a more detailed comparison of Greek philosophy with modern scientific concepts will be carried out below. Greek philosophy, through the teachings of Parmenides, returned for a time to the concept of the One. Parmenides lived in southern Italy. Apparently, his most significant contribution to Greek philosophy is the introduction of a purely logical argument into metaphysics. According to this argument, one cannot know what does not exist. There cannot be anything that cannot be expressed at the same time. What cannot be conceived cannot exist. Therefore, there exists only the One, and there is no becoming or destruction. Based on logical reasoning, Parmenides denied the existence of empty space, as any change implies the concept of empty space, and he dismissed all change as an illusion. However, philosophy could not remain on these paradoxes for long. Empedocles shifted from monism to one of the varieties of pluralism to resolve the difficulty that one of the primary elements does not provide a sufficient basis for explaining the diversity of things and events. He considered four fundamental elements: earth, water, air, and fire. These elements combine and separate under the influence of love and strife. Love and strife that condition eternal changes. He represented the four elements as something corporeal. Empedocles described the origin of the world as follows. First, there existed an infinite sphere of the One. This assertion coincides with a similar assertion in Parmenides' philosophy. Unlike Parmenides' first matter, Empedocles' matter is mixed under the influence of love of the four roots, or four elements. When love retreats, strife ensues. The elements are partially separated and partially reunited. Finally, the elements are completely separated, and love entirely disappears from the world. Then love returns and unites the elements, and strife vanishes, so that everything returns to its original state. Empedocles' doctrine, although it features somewhat unclear concepts of love and strife, represents a significant turn in Greek philosophy towards more concrete, and in this sense, materialistic notions. The four elements are not so much fundamental principles as they are material substances. This expresses for the first time the idea that the combination and separation of several fundamentally different substances explain the infinite diversity of phenomena. Pluralism will always prove unsatisfactory to those accustomed to sequential thinking. Principally, pluralism represents a reasonable compromise that eliminates the difficulties of monism while allowing for a certain order. The next step towards the concept of the atom was taken by Anaxagoras, a contemporary of Empedocles. He lived for about 30 years in Athens, likely in the first half of the 5th century BCE. Anaxagoras developed the idea that all changes in the world occur due to the combination and separation of various elements. He believed that there exists an infinite variety of infinitely small seeds from which all things are composed. These seeds have no relation to any of the four elements of Empedocles. On the contrary, there exists an infinite multitude of seeds. Seeds combine and separate, and thus change occurs. Anaxagoras provided a geometric interpretation of the term combination, as he spoke of infinitely small seeds. Their combination can be imagined as the joining of two grains of sand of different colors. Seeds can change in number and relative position. Anaxagoras believed that all seeds are present in all things, but only their relationship changes from body to body. He asserted that all things are in all things and cannot be completely separated from one another, but all things have some part of each other. Anaxagoras's universe is created not through love and strife, but through Janus, which translates roughly to two-faced. Only one step was needed to transition from philosophy to the concept of the atom, and this step was taken by Leucippus and Democritus. We have taken the polarity of being and non-being from Parmenides' philosophy, which has been replaced here by the polarity of the filled and the empty. Being is not just the one, it can be infinitely repeated. It consists of the smallest indivisible particles of matter, which are eternal and indestructible but possess finite size. Movement is impossible without the existence of empty space between atoms. Thus, for the first time in history, the idea of the existence of indivisible particles of matter as primary building blocks was expressed. We would say elementary particles. The concept of the atom, being indivisible, was reduced to the idea that matter consists not only of the filled, but also of the empty, namely, the empty space in which atoms move. The logical justification for Parmenides' objection to empty space, to the idea that non-being cannot exist, was simply ignored based on experience. From the perspective of modern science, we would say that the empty space between Democritus's atoms is not nothing. It serves as the carrier of geometry and kinematics and enables the order and movement of atoms. To this day, the possibility of empty space remains an unresolved problem in the general theory of relativity. Einstein showed that geometry and matter mutually condition each other. This response aligns with the view presented in many philosophical systems, which posits that space is defined by extended matter. Democritus retained the notion of empty space to be able to explain changes and movements. Democritus's atoms are the same substance that previously possessed one property, being, but they have different sizes and shapes, which means they can be considered divisible in a mathematical and physical sense. Atoms can move and occupy different positions in space, but they do not possess any other physical properties. They have no color, smell, or taste. The properties of matter, perceived by our senses, according to this view, are created by the arrangement of atoms in space and their movement. Just as comedy and tragedy can be written with the same letters of the alphabet, so the infinite diversity of events in the world is realized through the same atoms by virtue of their movement and configuration. This explains why, in the development of atomic philosophy, geometry and kinematics, conditioned by emptiness, had greater significance than pure being. As is well known, Democritus claimed that it only seems that things have color. It only seems that they are sweet or bitter. In reality, there exist only atoms and emptiness. The atoms of philosophy were not simply a chance occurrence. Leucippus apparently fully operated under the idea that nothing arises from nothing, and that everything arises from a specific cause and necessity. However, he did not provide any explanation for the origin and cause of the first impulse that initiates the original movement of atoms. This aligns well with their position on the causal description of atomic movement. Causality explains subsequent events through preceding ones, but can never explain the initial beginning. Subsequently, the main ideas of atomic doctrine were partially adopted and partially altered by later Greek philosophers. For comparison with modern atomic physics, Plato's understanding of matter, expressed in the dialogue Timaeus, is of interest. According to Diogenes Laertius, Plato disapproved of Democritus's philosophy to such an extent that he wished to burn his books. Yet, in his teachings, Plato combined ideas close to atomism with the concepts of the Pythagorean school and the philosophy of Empedocles. The Pythagorean school was associated with an archaic cult patronized by Dionysus. It was in the Pythagorean school that the connection between religion and mathematics was established, which has since exerted a powerful influence on human thought. Apparently, the Pythagoreans were the first to realize the creative power of mathematics. Their discovery that two strings produce harmonious sounds when their lengths are in a specific rational ratio demonstrated to them the significance of mathematics for understanding natural phenomena. Essentially, for them, it was not so much about rational understanding as it was about the mathematical relationship of string lengths creating harmony of sounds. Thus, the teachings of the Pythagoreans contained much mysticism, almost incomprehensible to us. But by making it part of their religion, they touched on a crucial point in the development of human thought. The English philosopher Bertrand Russell remarked about Pythagoras, "I do not know of any person who has had such an influence on human thought as Pythagoras." Plato was aware of the 5 regular geometric bodies discovered by the Pythagoreans, and that they could be correlated with the elements of Empedocles. He associated the smallest part of the earth element with the cube, the smallest part of the air element with the octahedron, the fire elements with tetrahedra, and the water elements with icosahedra. There was no element corresponding to the dodecahedron. Here, Plato stated that there exists a 5th element, which God used to create the universe. The regular geometric bodies can be compared in some respects to atoms. However, Plato categorically denied their indivisibility. He constructed his regular bodies from 2 types of triangles, equilateral and isosceles right triangles. By combining them, he obtained the faces of the regular bodies. This explains the partial increments of the elements to each other. Regular bodies can be decomposed into triangles, and from these triangles, new regular bodies can be constructed. For example, a tetrahedron can be decomposed into 20 equilateral triangles, and the latter can be recombined to form an icosahedron. That is, 1 atom of fire and 2 atoms of air combined yield 1 atom of water. Triangles cannot be considered matter, as they lack spatial extension. Only when triangles are united into regular bodies do particles of matter arise. Therefore, atoms are not primary formations, as they were in Democritus's view. They represent mathematical forms. It is clear that in this case, form is more significant than the substance from which the form is made or in which it is manifested. Now, after a brief overview of the development of Greek philosophy up to the formation of the concept of the atom, we will return to modern physics and ask how our contemporary understanding of the atom and quantum theory relates to the development of ancient natural philosophy. Historically, the word atom in physics and chemistry was initially associated with a false object. This occurred in the 17th century when the revival of the sciences began. At that time, atoms referred to parts of a chemical element, which from the perspective of modern science are quite complex formations, units that are even smaller than the atom of a chemical element. Today, they are called elementary particles. If anything from modern physics can be compared to Democritus's atoms, it is elementary particles, protons, neutrons, and electrons. Democritus was fully aware that if atoms explain the properties of matter, such as color, taste, and smell, through their movement and configuration, then they themselves cannot possess these properties. Therefore, Democritus stripped atoms of these properties, and the atoms of Democritus represent a rather abstract unit of matter. Democritus's atoms possess the properties of existence and movement, have form and spatial extension. Without these properties, it would be difficult to speak of an atom. Hence, the concept of the atom does not explain the geometric form, spatial extension, and existence of matter, as these properties are presupposed and are not reducible to anything more primary. The modern understanding of elementary particles addresses these questions more consistently and radically. For example, we use the term neutron very easily, but we cannot provide any specific image of a neutron and cannot say what exactly we understand by this word. We use various images and represent the neutron either as a particle or as a wave or wave packet. Yet we know that none of these descriptions is accurate. Clearly, a neutron has no color, smell, or taste, thus resembling the atoms of Greek philosophy. However, elementary particles are in some respects devoid of other properties as well. Common notions of geometry and kinematics regarding particles, such as shape or movement in space, cannot be applied to elementary particles. If one wishes to provide an accurate description of an elementary particle, here we emphasize the word accurate. The only thing that may be suitable as this description is a probability function. From this, it follows that, in general, when it comes to properties, the property of being does not apply unconditionally to elementary particles. There is only a tendency, a possibility of being. Therefore, the elementary particles of modern physics are significantly more abstract than the atoms of the Greeks, and for this reason, they do not provide a more suitable key for understanding the nature of matter. In Democritus's philosophy, all atoms consist of the same substance, matter. Since this word can generally be applied here, the elementary particles of modern physics have mass. According to the theory of relativity, mass and energy are essentially the same, and therefore one can say that all elementary particles consist of energy. Thus, energy can be considered the primary substance of primordial matter. In fact, it possesses a significant property belonging to the concept of substance. It is conserved. On this basis, as already mentioned, the representation of modern physics is very similar to the views of Heraclitus, if one interprets the element fire as energy. Energy is movement. It is regarded as the ultimate cause of all changes and can be converted into matter, heat, and light. The struggle of opposites, characteristic of Heraclitus's philosophy, finds its prototype here in the interaction of various forms of energy. In Democritus's philosophy, atoms are eternal and indivisible units of matter. They cannot transform into one another. Modern physics opposes Democritus's position and aligns itself with Plato and the Pythagoreans. Elementary particles are not eternal and indivisible units of matter. In fact, they can transform into one another. When two elementary particles collide at high speed, many new elementary particles are created from the energy of motion. The colliding particles may disappear in the process. Such events are frequently observed and serve as the best evidence that all particles consist of the same substance, energy. However, the similarity of modern physics views to those of Plato and the Pythagoreans extends even further. The elementary particles mentioned in Plato's dialogue Timaeus are, after all, not matter, but mathematical forms. All things are numbers. The position attributed to Anaxagoras is that the only mathematical forms known at that time were geometric and stereometric forms, such as regular bodies and triangles that make up their surfaces. In modern quantum theory, there is little doubt that elementary particles ultimately are mathematical forms, only of a much more complex and abstract nature. The Greek philosophers thought of static geometric forms and found them in regular bodies. Natural science in the modern era, at its inception in the 16th and 17th centuries, made the problem of motion its central issue. Consequently, it introduced the concept of time into its foundation. Since the time of Newton, physicists have investigated not configurations or geometric forms, but dynamic laws. The equations of motion pertain to any moment in time. In this sense, it is eternal, while geometric forms, such as the orbits of planets, change. Therefore, the mathematical forms representing elementary particles must ultimately be a solution to the unchanging law of motion of matter. In the following years, the development of physics reached a state where physicists began to strive to formulate a fundamental law for matter. Experimental physics gathered a substantial amount of data on the properties of elementary particles and their transformations. Theoretical physics can attempt, based on this material, to derive a fundamental law for matter. Earlier, a simple form of this equation of matter was proposed, although it will only become clear in the future how accurate this equation is. Nevertheless, this is the first attempt that shows such features of physics and philosophy that can likely be established from the study of elementary particles. At least qualitatively, this attempt should be described here in the problem of the fundamental equation. It concerns a nonlinear wave equation for field operators. At this level, it does not consider a mathematical representation of all matter or any specific type of elementary particles or fields. This wave equation is mathematically equivalent to a complex system of integral equations, which, as mathematicians say, possess eigenvalues and eigenfunctions. The eigenfunctions represent elementary particles. Thus, they are mathematical forms that replace the regular bodies of the Pythagoreans. Incidentally, it should be noted that the eigenfunctions of the fundamental equation are obtained through a mathematical procedure, similar to how harmonic oscillations of a stretched string are derived from the differential equation of the string, as described by the Pythagoreans. The mathematical symmetry, which plays a central role in the regular bodies of Plato's philosophy, forms the core of the fundamental equation. The equation is merely a mathematical representation of the entire array of symmetry properties, which, of course, are not as visually apparent as Plato's bodies. In modern physics, the discussion revolves around symmetry properties related to space and time, which find their mathematical expression in the group structure theory of the fundamental equation. The most important group is the so-called Lorentz group in the theory of relativity, which defines the structure of space and time. Additionally, there are other groups that have only recently been discovered and are associated with various quantum numbers of elementary particles. Although the fundamental equation itself has a relatively simple form, it contains a large number of different symmetry properties, and apparently the rich experimental material on the transformations of elementary particles corresponds precisely to these symmetry properties. Therefore, modern physics is advancing along the same path that Plato and the Pythagoreans took. This development in physics appears to suggest that at its conclusion, a very simple formulation of the law of nature will be established, as simple as Plato hoped to see. It is difficult to point to any solid foundation for this hope for simplicity, apart from the fact that until now, the fundamental equations of physics have been expressed in simple mathematical formulas. This fact aligns with the religion of the Pythagoreans, and many physicists share their belief in this regard. However, to this day, no one has provided truly convincing evidence that this must be the case. One can present considerations regarding a question often posed by amateurs concerning the concept of elementary particles in modern physics. Why do physicists say that elementary particles cannot be decomposed into smaller particles? The answer to this question clearly illustrates how much more abstract modern natural science is compared to Greek philosophy. Our reasoning in this regard is roughly as follows. How can one decompose elementary particles? The only experimental means at our disposal are other elementary particles. Therefore, the collision of two elementary particles with extremely high kinetic energy represents the only processes in which such particles may be decomposed. We do not disintegrate in such processes, sometimes even into many different parts. However, the constituent parts are again elementary particles, not some small fragments. Their masses are formed from the kinetic energy of the colliding particles. In other words, due to the conversion of energy into matter, the constituent parts of elementary particles are again elementary particles of the same type. After such a comparison of modern atomic physics with Greek philosophy, we must issue a warning that would eliminate the possibility of misunderstanding. At first glance, all this may seem as if Greek philosophers, through their genius, arrived at the same, or at least very similar results to those we have achieved in modern times after several centuries of arduous work in experimentation and mathematics. However, such an interpretation of our comparison carries the danger of gross misunderstanding. There is a significant difference between modern natural science and Greek philosophy, one of the most important being the empirical foundation of modern natural science. Since the time of Galileo and Newton, natural science has been based on the careful study of individual processes in nature and on the requirement that one can only make statements about nature that are confirmed by experiments. The idea that one can isolate processes in nature through experimentation to study them in detail and uncover the unchanging laws contained within constant change did not arise among Greek philosophers. Therefore, modern natural science rests on a more modest and more solid foundation than ancient philosophy. If, for example, Plato stated that the smallest particles of fire are tetrahedra, it is not easy to assume that he actually thought symbolically, whether the shape of the tetrahedron belongs to the element of fire, or whether the smallest particles of fire behave mechanically like rigid or elastic tetrahedra, and by what force they can be decomposed into the triangles that Plato described. Modern natural science would finally have to ask how one can experimentally determine that the atoms of fire are tetrahedra and cannot be anything else, such as cubes. Therefore, if modern field theories assert that a proton is represented by a specific eigenfunction of the fundamental equation of matter, it means that from this solution, all possible properties of the proton are mathematically derived, and the correctness of the solution can be proven in each individual case through experimentation. The ability to experimentally verify the accuracy of a statement with very high precision gives the statement of modern physics significantly greater weight than that possessed by the statements of ancient natural philosophy. Yet some statements of ancient philosophy are remarkably close to those of modern natural science. This shows how far one can go if one connects our ordinary experience, unsupported by experiments, with the relentless effort to create a logical order in experience and to attempt to understand it based on general principles. It has been pointed out repeatedly that sometimes natural science concepts can be defined in relation to their connections exhaustively. This possibility was clearly revealed for the first time in Newton's Principia. For this reason, Newton's work had a tremendous influence on the development of natural science in the subsequent centuries. Newton begins his exposition with several definitions and axioms that are interconnected in such a way that something can be called a closed system arises. Each concept can be assigned a mathematical symbol, and then the relationships between different concepts are represented in the form of mathematical equations that can be written using these symbols. The mathematical representation of the system ensures the impossibility of contradictions arising within the system. Thus, the motion of bodies under the influence of forces can ultimately be represented as possible solutions to a mathematical equation and a system of equations. The system of definitions and axioms, which can be expressed in the form of a certain number of equations, is regarded in this case as a description of the unchanging structure of nature, which cannot depend on the specific place where the process occurs, or the specific time, and, therefore, has validity, so to speak, generally, independently of space and time. The connection of various concepts within the system is so close that it is impossible to change any of these concepts without simultaneously destroying the entire system. On this basis, Newton's system was long regarded as definitive. Science believed that its task was only to apply Newtonian mechanics to increasingly broader areas of experience. In fact, physics developed for almost 2 centuries only in this direction. From the theory of motion of a material point, one could transition to the mechanics of solid bodies, rotational motion, as well as to the consideration of continuous motion of fluids or oscillatory movements of elastic bodies. All these branches of mechanics were gradually developed as mathematics, particularly differential calculus, advanced, and the results were verified through experiments. Acoustics and hydrodynamics became branches of mechanics. Another science to which Newtonian mechanics could be successfully applied was astronomy. The improvement of mathematical methods led to increasingly precise determinations of the movements of planets and their mutual perturbations. After the discovery of new phenomena in electricity and magnetism, electric and magnetic forces were likened to gravitational forces, and their influence on the motion of bodies could again be accounted for using the axioms of Newtonian mechanics. Finally, in the 19th century, even the theory of heat was reduced to mechanics based on the assumption that heat is, in fact, a complex statistical motion of the smallest particles of matter. By combining the concepts of Newtonian mechanics with the concepts of mathematical probability theory, Clausius, Gibbs, and Boltzmann managed to show that the fundamental laws of thermodynamics can be interpreted as statistical laws derived from Newtonian mechanics when applied to very complex mechanical systems. Thus, up to this point, the problems posed by Newtonian mechanics were consistently addressed, making it possible to understand a very broad area of experience. The first difficulty arose when considering the electromagnetic field in the works of Faraday and Maxwell. In Newtonian mechanics, gravitational force was considered something given, not a subject for further theoretical investigation. However, in the works of Faraday and Maxwell, the force field itself became the object of study. Physicists sought to understand how this field, the force field, changes as a function of spatial coordinates and time. Therefore, they attempted to find the equation of motion for the field and the elementary laws of motion for the bodies acted upon by the field. This returned to the concepts prevalent in the era preceding the establishment of Newtonian mechanics. Action, it seemed, could only be transmitted from one body to another when both bodies touch each other, for example, during a collision or through friction. Newton, on the other hand, proposed the existence of a force acting at great distances, namely gravitational force. He introduced a new and very remarkable way of transmitting the action of forces into physics. Now, in the theory of force fields, it was possible, in a certain sense, to return to older notions that action is always transmitted only from point to adjacent point. Mathematically, this would require describing the behavior of fields with differential equations. This turned out to be indeed possible, and thus the description of the electromagnetic field provided by Maxwell using known equations was considered a satisfactory solution to the problem of forces or force fields. However, at this point, the program prescribed at one time by Newtonian mechanics was actually modified. Newton's axioms and definitions pertain to bodies and their motion, whereas in Maxwell's theory, force fields acquired the same degree of reality as bodies in Newtonian theory. This new understanding was not accepted immediately and without objections. To avoid such changes in our perceptions of reality, electromagnetic fields were attempted to be compared with the fields of elastic deformations and tensions, and thus the light waves of Maxwell's theory with sound waves in elastic bodies. Therefore, many physicists believed that the equations of Maxwell actually pertained to deformations of an elastic medium, which they called ether. This term was used only to emphasize that the medium is so light and rarefied that it permeates other substances and cannot be invisible or imperceptible. Such an explanation was, of course, not very satisfactory, as it did not account for why there are no longitudinal oscillations in light. Finally, the theory of relativity, which will be discussed in the next chapter, convincingly demonstrated that the concept of ether as a substance related to Maxwell's equations should be abandoned. The arguments proving this conclusion cannot be detailed here. As a result, there arose, in any case, the necessity to regard fields as an independent reality. Furthermore, an even more troubling conclusion of the special theory of relativity was the discovery of new properties of space and time, or, more accurately, the relationships between space and time, relationships that had not been known before, and therefore had no place in Newtonian mechanics. Under the impression of this completely new situation, many physicists prematurely concluded that Newtonian mechanics has now been definitively refuted. The primary reality is supposedly fields, not bodies, and the structure of space and time is accurately described by Einstein's Lorentz formulas. They consider Newtonian mechanics to be valid only as a good approximation, which, however, now needs to be improved to make way for a more rigorous and precise description of nature. But such a claim, from the general perspective finally reached from quantum theory, should be regarded as completely unsatisfactory. It is an inadequate representation of the actual state of affairs. For, firstly, this assertion overlooks the fact that most experiments measuring fields are based on the application of Newtonian mechanics. And secondly, Newtonian mechanics, in fact, cannot be improved. It can only be replaced by something fundamentally different. The development of quantum theory has shown that a more accurate position can be described in the following words. Wherever the concept of Newtonian mechanics can be applied to describe processes in nature, the laws formulated by Newton are also valid and cannot be improved. Electromagnetic phenomena cannot be adequately described using the concepts of Newtonian mechanics. Therefore, experiments on electromagnetic fields and light waves, along with their theoretical analysis conducted by Maxwell and Einstein, led to a new closed system of definitions, axioms, and concepts that can be represented using mathematical symbols. This system is as consistent and closed as Newton's system of mechanics, although it is fundamentally different from Newton's framework. Consequently, even the expectations that accompanied Newton's work must now be revised. The progress of science clearly cannot always be tied to the application of known laws of nature to explain new phenomena. In some cases, the observed new phenomena can only be understood using new concepts that correspond to new observed facts in the same way that Newtonian concepts corresponded to mechanical processes. New concepts can again be linked into a closed system and expressed using mathematical symbols. However, if the progress of physics, or more broadly, natural sciences, moves in this direction, the question arises regarding the relationship between different systems of concepts. For example, if the same concepts and words exist in two different systems and are defined in relation to their interconnections differently, in what sense can we say that these concepts reflect reality? This issue arose at the time when the theory of relativity was being developed. The concepts of space and time are necessary for both Newtonian mechanics and the theory of relativity. But in Newtonian mechanics, space and time are independent of each other, while in the theory of relativity, they are interconnected through Lorentz transformations. In this specific case, it can be shown that the assertion of the theory of relativity in the limiting case when the speeds of the bodies in the system are very small compared to the speed of light reduces to the assertion of Newtonian mechanics. This leads to the conclusion that the concepts of Newtonian mechanics cannot be applied to processes where mechanical speeds are comparable to the speed of light. Thus, a significant limitation on the applicability of Newtonian concepts has ultimately been found, which cannot be discerned within this closed system of concepts or through observations solely of mechanical systems. Therefore, the relationship between two different closed systems of concepts always requires very careful investigation. Before proceeding to a general discussion of the structure of such closed and interconnected systems of concepts and their possible relationships, it is necessary to briefly list the systems of concepts that have been defined and developed by physicists up to the present time. Nowadays, 4 major systems can be distinguished, each having reached its final form. The first system is Newtonian mechanics, which has already been discussed. It is suitable for describing all mechanical processes, fluid motion, and the elastic oscillations of bodies. It includes acoustics, statics, aerodynamics, and hydrodynamics. Astronomy, to the extent that it deals with the movements of celestial bodies, also belongs to this system. The second closed system emerged in the 19th century, the theory of heat. Although ultimately, the theories of heat managed to connect with mechanics through the development of so-called statistical mechanics, it would be better not to consider this system as part of mechanics, since at least in phenomenological theory of heat, a number of concepts are used that have no analogues in other branches of physics, namely, the concepts of heat, specific heat, entropy, free energy, and so forth. If we transition from this phenomenological description to a statistical one, considering heat as energy statistically distributed across many degrees of freedom of the system, determined by the atomic structure of matter, then the theory of heat turns out to be related to mechanics no more than to electrodynamics or any other branches of physics. The central concept of such a statistical interpretation of the theory of heat is the concept of probability, closely tied to the concept of entropy in phenomenological theory. Alongside this, the concepts of energy also play a crucial role in statistical theory of heat. But any closed and unchanging system of definitions and axioms in physics must also contain the concepts of energy, momentum, angular momentum, as well as the requirement that these quantities must be conserved under certain external conditions. The latter occurs, as more precise investigation shows, only when the closed system must describe features of nature that pertain to all moments of time and position. In other words, features that do not depend on coordinates and time, or, as mathematicians express it, are invariant with respect to certain shifts in space and time, rotations in space, or Galilean or Lorentz transformations. Thus, theories of heat can be related to any other closed systems of concepts in physics. The third closed system of concepts was derived from electrical and magnetic phenomena, reaching its final form in the first decade of the 20th century in the works of Lorentz, Einstein, and Minkowski. It encompasses electrodynamics, special relativity, optics, magnetism, and can even include de Broglie's narrow theory of matter waves, applicable to all elementary particles of various kinds. However, Schrödinger's wave mechanics does not belong to this system. Finally, the fourth closed system is quantum theory, with its central concept being the probability function, or, to use a more rigorous mathematical language, the statistical matrix. This system encompasses quantum and wave mechanics, atomic spectrum theory, chemistry, and the theory of other properties of matter, such as conductivity, magnetism, and so forth. The relationship between these 4 closed systems of concepts can perhaps be outlined as follows. The first system is contained within the third as a limiting case when the speed of light can be considered infinite. It is also contained within the fourth as a limiting case when Planck's quantum of action can be considered infinite. The first and partly the third systems are necessary for the fourth as a priori foundations for describing experiments. The second system can be easily linked to each of the other 3, and is especially important in conjunction with the fourth. The independence of the existence of the third and fourth systems suggests the possibility of a fifth closed system of concepts in which the first, third, and fourth are contained as limiting cases. This fifth system will someday be discovered in connection with the theory of elementary particles. In this enumeration of closed systems of concepts, we have set aside the general theory of relativity, as this system of concepts has not yet found, perhaps, its final form. However, it should be noted that it is distinctly different from the other four systems. After this brief overview, let us return to the more general question of what should be considered as the foundation of such closed systems of axioms and definitions. The most important feature is perhaps that a consistent mathematical representation of the system can be found. Such a representation guarantees that the system itself contains no internal contradictions. Furthermore, the system must be suitable for describing a wide range of experiences. The variety of phenomena in the area under consideration must correspond to a variety of solutions permitted by the equations. The mathematical schemes that define the boundaries of this area of experience cannot, generally speaking, be derived from concepts. Concepts are not strictly defined in relation to their correlation with nature, in contrast to their strict definition in relation to their possible interconnections. Therefore, the boundaries of the applicability of concepts must be determined empirically. That is, simply from the fact that these concepts, starting from certain points, are no longer sufficient for a complete description of the observed phenomena. Following this brief analysis of the structure of modern physics, we should discuss its relationship with other branches of natural science. The closest neighbors of physics are chemistry. In fact, these two sciences have merged thanks to quantum theory, contributing to a unified understanding. But 100 years ago, they were still quite distant from each other. Their research methods were completely different, and the concepts of chemistry at that time had no analogous concepts in physics. Concepts such as valence, activity, solubility, or volatility were more qualitative in nature, and chemistry at that time was hardly a precise science. Once the theory of heat was developed in the middle of the last century and began to be applied to chemical processes, scientific work in this area was characterized by the hope that one day the laws of chemistry could be reduced to atomic mechanics. However, it is essential to emphasize that within the framework of Newtonian mechanics, this proved impossible. To provide a quantitative description of chemical laws, it was necessary to formulate a significantly deeper system of concepts in atomic physics. This was ultimately achieved in quantum theory, whose roots thus lie in chemistry to the same extent as in atomic physics. Furthermore, it became clear that chemical laws could not simply be reduced to Newtonian mechanics of atomic particles, as chemical elements exhibit a degree of stability in their behavior that is entirely uncharacteristic of mechanical systems. However, it was only in Bohr's atomic theory of 2013 that this perspective was articulated very clearly. As a final result, one can establish, for example, that chemical concepts, in a certain sense, are supplementary to mechanical concepts. If we know that an atom is in a lower energy state, determining its chemical behavior, we cannot simultaneously speak of the motion of electrons within that atom. The modern relationship between biology on one side and physics and chemistry on the other may bear a certain resemblance to the relationship between chemistry and physics 100 years ago. The methods of biology are quite different from those of physics and chemistry, and atypical biological concepts are more qualitative than the concepts of the exact natural sciences. Concepts such as life, organ, cell, organ function, and sensations have no counterparts in physics or chemistry. On the other hand, the significant progress made in biology over the past 100 years has been achieved through the application of the laws of physics and chemistry to living organisms, and all contemporary biological efforts are directed towards explaining biological phenomena based on known physical and chemical laws. Here arises the question, is this hope justified? Just as in chemistry previously, it is now recognized based on the simplest biological experiments that living organisms exhibit a degree of stability that complex structures composed of many different molecules cannot possess solely based on physical and chemical laws. Therefore, something must be added to the physical and chemical laws before biological phenomena can be fully understood. In this regard, two distinctly different viewpoints are often discussed in biological literature. One of them refers to Darwin's theory of evolution in relation to modern genetics. According to this theory, the only concept that needs to be added to physics and chemistry to understand life is the concept of history. The vast period of time, approximately 4 billion years, that has elapsed since the formation of the Earth has allowed nature to explore almost limitless varieties of molecular group structures. Among these structures, those eventually emerged that could themselves become more complex based on smaller groups of surrounding matter, and such structures could therefore be created in large numbers. Random changes in structures led to even greater diversity of existing structures. Different structures competed for substances that could be utilized from the surrounding matter. Thus, through Darwinian selection, through the survival of the fittest, the development of living organisms ultimately took place. There is little doubt that this theory contains a significant degree of truth, and many biologists assert that to explain all biological phenomena, it is entirely sufficient to add the concept of history and development to the closed system of concepts of physics and chemistry. One of the arguments often presented in favor of this theory emphasizes that everywhere the laws of physics and chemistry can be tested, they always prove to be valid concerning living organisms. It seems impossible to point to a single instance where one could discover the actions of a special vital force, distinct from known forces in physics. On the other hand, this argument has lost much of its persuasive power due to the development of quantum theory, as the concepts of physics and chemistry form a closed and consistent system, namely, the system of quantum theory. It necessarily follows from this that wherever these concepts can be applied to describe phenomena, they must hold true. The laws associated with these concepts must always behave as such when living organisms are considered as physical and chemical systems. The only question regarding the validity of this viewpoint is whether the concepts of physics and chemistry allow for a complete description of organisms. Biologists, in answering this question, generally lean towards the second viewpoint, which we will now examine. This second viewpoint can perhaps be described as follows. It is difficult to imagine that concepts such as sensation, organ function, inclination, and so forth should belong to a closed system of concepts of quantum theory, even when linked to the concept of history. On the other hand, these named concepts are undoubtedly necessary for a complete description of life, even when primarily considering humans, as the existence of a human raises issues that extend beyond biology. Therefore, to understand the processes of life, it is likely necessary to go beyond quantum theory and construct a new closed system of concepts, of which physics and chemistry may later become limiting cases. History may prove to be a significant part of this system, and concepts such as sensation, adaptation, and inclination will also be included. If this viewpoint is correct, then the connection between Darwin's theory and physics and chemistry will be insufficient to explain organic life. However, it will always remain true that living organisms, in a broad sense, can be regarded as physical and chemical systems, as machines in the formulation of Descartes and Laplace. This means that if they are viewed as machines, they will behave as such. Simultaneously, it could be accepted, as Bohr suggested, that our knowledge that a cell is alive may be something additional to the complete knowledge of molecular structures, as complete knowledge of this structure can likely only be achieved through an intervention that destroys the life of the cell. It is logically possible that life excludes the complete establishment of the underlying physical and chemical structures. But even if this second viewpoint is deemed correct, it is unlikely that biological research can be recommended to pursue any path other than that which has led to most successes over the past centuries. It is necessary to attempt, as much as possible, to explain everything based on known physical and chemical laws, and the behavior of organisms must be described thoroughly and without theoretical biases. The first of these viewpoints is more widely held among contemporary biologists than the second, but the experimental material currently available is unlikely to be sufficient to definitively choose one over the other. The preference that many biologists show for the first viewpoint may be an indirect consequence of the Cartesian division that has profoundly influenced human thought over the last centuries. Since the thinking being was understood to be only a human, animals, which have their own I, could not possess souls. They were regarded solely as extended beings. Hence, it follows that the same research methods applicable to matter in general could be applied to the study of animals, and that the laws of physics and chemistry, along with the concept of history, should suffice to explain their behavior. If now the thinking being, according to Descartes, is included in the consideration, a completely new situation arises, requiring entirely new concepts. However, the Cartesian division is a dangerous simplification, and therefore it is quite possible that the second viewpoint is correct. Regardless of this unresolved question, we seem to be still very far from a closed and consistent system of concepts for describing biological phenomena. The degree of complexity in biology is so daunting that it is currently difficult to imagine how any closed system could be created, the concepts of which are defined so clearly that mathematical representation becomes possible. If we extend beyond biology and include psychology in the discussion, it is hard to doubt that the concepts of physics and chemistry, along with the concepts of developmental theory, are still insufficient to explain and describe the facts of psychology. In this regard, the emergence of quantum theory has decisively altered our perspective compared to the views of the 19th century. At that time, some scientists were inclined to believe that the facts of psychology could ultimately be explained by the physics and chemistry of the human brain. From the standpoint of quantum mechanics, there are no longer any grounds for such assumptions, although physical processes in the brain are related to mental processes. Yet, it cannot be assumed that these physical processes are sufficient to explain mental phenomena. Naturally, we would not doubt that the brain behaves as a physical chemical mechanism when considered as such. However, to understand mental phenomena, one should start from the fact that in this case, the human spirit appears in psychology as both an object and a subject of scientific inquiry. If we now review once more the various closed systems of concepts that have been created in the past or may be created in the future for scientific research, it is noteworthy that these systems seem to be arranged in a direction of increasing contribution of subjective elements to the system of concepts. Classical physics can be seen as an idealization in which we speak of the world as something entirely independent of ourselves. The first three systems of concepts correspond to this idealization. Only the first of these systems fully aligns with the concept of a priori in Kantian philosophy. In the fourth system of concepts, quantum theory, humans emerge as subjects of science due to the questions posed to nature that must be formulated in the a priori concepts of humanity. Natural science, through quantum theory, no longer allows for a completely objective description of nature. In biology, for the sake of completeness, it is important to keep in mind that the questions are formulated by the biological species, humans, who themselves belong to the category of living organisms. In other words, what we already know about what life is, even before it receives a scientific definition. However, it seems unnecessary to elaborate on purely speculative considerations regarding the possible structure of systems of concepts that have not yet been constructed. If this order or arrangement is compared with older classification systems from earlier epochs of natural science, it is remarkable that in such cases the world is divided not into different groups of objects, but into different groups of relationships. In one earlier period of natural science, for example, minerals, plants, animals, and humans were distinguished. These objects were viewed within each of their groups as having different natures, formed from different substances, and defined in their behavior by the actions of various forces. Now we know that ultimately there is always the same substance, the same chemical compounds of various kinds that can make up any arbitrary object, minerals, just as much as animals or plants, and the forces acting between different parts of matter are essentially the same across various objects. What can truly be distinguished is the type of relationships that are most significant for specific phenomena. For example, when we speak of the action of chemical forces, we refer to a type of relationship that is more complex or, in any case, different from that given in Newtonian mechanics. The world appears from this perspective as a complex intertwining of processes, where a wide variety of relationships change, intersect, and act together, thereby defining the structure of the entire weave. If we describe a group of relationships using a closed and interconnected system of concepts, axioms, definitions, and laws, which can in turn be represented in the form of a material scheme, we effectively isolate and idealize this group of relationships for the purpose of scientific study. However, even if complete clarity is achieved, it remains unknown how accurately this system of concepts corresponds to reality. This idealization can also be considered a part of human language, which has arisen in the course of our two-way interaction with the world as a response of humanity to the demands of nature. From this perspective, the idealization can be compared, for example, to different styles in art, such as architectural or musical styles. A style can be defined as a system of formal rules applied to the material by various forms of art. Although these rules cannot be satisfactorily represented through a system of mathematical concepts and equations, their fundamental elements are still very much akin to the basic elements of mathematics or mathematical descriptions of nature: equality, inequality, repetition, and symmetry. Certain group structures play a fundamental role in usage, just as in mathematics. Typically, the development of a formal system that constitutes a style in art requires the work of several generations to evolve from its simple initial techniques to the richness of more complex forms that characterize the completion of the style. The artist's interest focuses on this process of crystallization, in which the material of art, through their activity, takes on various forms brought to life by the initial formal concepts of that style. In art, after the development is completed, the interest necessarily diminishes, as the word interest means being involved in something, participating in the creative process. At that point, this process reaches its conclusion. Here, too, it cannot be determined based solely on the most formal rules how accurately the rules of style represent the reality of life intended in works of art. Art is always a certain idealization. The ideal is always distinct from reality, at least from the reality of shadows, as Plato said. But idealization is a necessary prerequisite for understanding. This comparison of different systems of concepts in natural science with various styles in art, when considering the latter as rather arbitrary creations of the human spirit, may seem quite erroneous. One could, for example, argue that different systems of concepts in natural science reflect the objective reality presented to us by nature, and that therefore they contain no arbitrariness, but rather represent necessary consequences of our ever-growing understanding of nature through experimentation. In this, most natural scientists would likely agree. But are different styles in art merely arbitrary creations of the human spirit? Here, the Cartesian division between the thinking being and extended beings must also be considered. Style arises from the mutual interaction between the world and ourselves, or more precisely, between the spirit of the time and the artist. The spirit of the time is likely as objective a factor as any fact of natural science, and this spirit reveals certain features of the world that are independent of time and can thus be called eternal in this sense. The artist attempts to make these features understandable in their work, and in this attempt, they arrive at the forms of style in which they work. Therefore, both processes in science and art are not so different. Over the centuries, science and art have formed a human language through which we can discuss the more remote aspects of reality, and the interconnected systems of concepts represent, just like various styles in art, to a certain extent, only different words or groups of words in this language. The theory of relativity has always played a particularly important role in modern physics. It was the first to demonstrate the necessity of periodically changing the fundamental principles of physics. Thus, discussions of the problems raised and partly resolved by the theory of relativity are essential for considering the philosophical aspects of modern physics. In a certain sense, one could say that the creation of the theory of relativity, in contrast to quantum theory, required relatively little time from the moment the difficulties in question were finally recognized to their resolution. The repetition of the Michelson, Morley, and Miller experiments in 1904 provided the first reliable evidence of the impossibility of detecting the Earth's translational motion using optical methods, and Einstein's decisive work appeared less than 2 years later. On the other hand, the Morley and Miller experiment and Einstein's work were still, perhaps, merely the last phases of a development that began much earlier and can be linked to the problem of electrodynamics of moving media. Electrodynamics of moving media has been an important area of physics and engineering since the construction of electric motors began. A significant difficulty emerged in this field only when Maxwell revealed the electromagnetic nature of light waves. These waves differ from other previously known waves, such as sound waves, by one essential property: they can propagate in empty space. If a bell is made to sound in a vessel from which air has been evacuated, the sound does not reach the space outside the vessel. Light, however, passes freely through a vacuum. Therefore, it was assumed that light waves could be regarded as elastic waves in a very light substance called the ether, which could not be seen or felt, but fills both empty space and the space occupied by other substances, such as air or glass. The idea that electromagnetic waves possess their own reality independently of any bodies had not yet occurred to physicists at that time. Since this hypothetical substance, ether, could penetrate all other bodies, the question arose: what happens if a body is set in motion? Does the ether participate in this motion? And if so, how does a light wave propagate in this moving ether? The experiments that provide answers to this question are challenging for the following reason. The speeds of moving bodies are usually extremely small compared to the speed of light, so the motion of these bodies can only produce a very slight effect, approximately proportional to the ratio of the body's speed to the speed of light, or a higher power of this ratio. Various experiments by Wilson, Rowland, Röntgen, and Finwald allowed for the measurement of such first-order effects with precision corresponding to the first degree of this ratio. The electronic theory developed by Lorentz in 1895 provided a satisfactory description of these first-order effects. However, the Michelson-Morley and Miller experiment created a new situation. This experiment deserves detailed discussion to achieve larger effects and thus more accurate results. It seemed reasonable to experiment with bodies moving very quickly. The Earth moves around the Sun at a speed of about 30 kilometers per second. If the ether is at rest relative to the Sun and is not dragged along with the Earth, this rapid motion of the ether relative to the Earth must necessarily manifest itself in a change in the speed of light on Earth. Different values of the speed of light should then be obtained depending on whether light propagates in the direction of the Earth's motion or perpendicular to it. Even if the ether is dragged along with the Earth, some effect should still occur, as there would be, so to speak, an ether wind, and this effect should then likely depend on height. Above sea level, where the experiment is conducted, the calculation of the effect that is to be expected shows that it should be very small in this case, as it turns out to be proportional to the square of the ratio of the Earth's speed to the speed of light. Therefore, precise experiments on the interference of two light beams, one directed parallel and the other perpendicular to the direction of the Earth's motion, are necessary. The first experiment of this kind, carried out by Michelson in 1881, was not sufficiently accurate, but subsequent repeated experiments found no trace of the expected effect. Thus, the definitive proof that the effect of the expected order of magnitude does not take place is, in particular, the experiment conducted by Morley and Miller in 1904. Their result initially seemed puzzling, but it relates to another question that had already been discussed by physicists shortly before. In Newtonian mechanics, a certain principle of relativity holds true, which can be characterized by the following words. If, in a specific reference frame, the laws of Newtonian mechanics apply to the mechanical motion of a body, then this is also true in any other reference frame that moves uniformly and in a straight line relative to the first frame. Thus, uniform linear motion does not produce any mechanical effects in this system, and therefore these effects cannot serve as a means of detecting such motion. Such a principle of relativity, as it seemed to physicists, could not be valid in optics and electrodynamics, because if the first system is at rest relative to the ether, then the moving system, on the contrary, is not at rest. It follows that the motion of this second system, relative to the ether, can be observed through effects of the kind investigated by Michelson. Therefore, the negative result of the Morley and Miller experiment in 1904 allowed for the revival of the idea that such a principle of relativity might also be valid in electrodynamics, just as it had been in Newtonian mechanics. On the other hand, there was the old experiment by Fizeau in 1851, which seemed to directly contradict this principle of relativity. Fizeau investigated the speed of light in a moving fluid. If the principle of relativity were valid, then the total speed of light in the moving fluid should equal the sum of the speed of the fluid and the speed of light in a stationary fluid. However, this was not the case. Fizeau's experiment showed that the total speed was somewhat less than the indicated sum. Despite this, the negative result of all recent attempts to detect motion relative to the ether prompted physicists and mathematicians to seek a mathematical interpretation of these experiments that could reconcile the wave equation for the propagation of light with the principle of relativity. Consequently, Lorentz proposed a mathematical transformation in 1904 that satisfied this requirement. He had to derive the hypothesis that moving bodies contract in the direction of their motion, with the contraction coefficient depending on the speed of the body, as well as that different reference frames measure different apparent time intervals, which in many experiments play the same role that real-time intervals had played until then. Following this path, he was able to arrive at results consistent with the principle of relativity. The apparent speed of light was now the same in every reference frame. Similar ideas were discussed by Poincaré, Fitzgerald, and other physicists. A decisive step was taken in 1905 by Einstein, who interpreted Lorentz transformations as transformations of real time, excluding from consideration the time that Lorentz called true. This meant a change in the foundations of physics, a completely unexpected and radical change that required the courage of a young revolutionary genius to take this step. In terms of the mathematical description of nature, it was only necessary to apply Lorentz transformations to experiments in a non-contradictory manner. However, due to the new interpretation of this transformation, physicists' views on the structure of space and time changed, and many problems in physics appeared in a new light. The ether substance, for example, turned out to be unnecessary and could simply be removed from the physics textbook, since in this case all reference frames, which are in uniform and straight-line motion relative to one another, are equivalent to each other when describing nature. Therefore, it no longer makes any sense to assert that there exists such an ether substance that is supposedly at rest in one specific reference frame. In fact, it no longer makes sense to consider such a substance, and it is much simpler to say that light waves propagate in empty space, and that electromagnetic fields possess their own reality and can exist in empty space. However, the decisive change affects the structure of space and time. It is very difficult to describe this change in ordinary language without using mathematics, as the ordinary words space and time already pertain to a structure of space and time that represents an idealization and simplification of the actual structure. Nevertheless, it is necessary to attempt to describe the new structure, and perhaps this can be done as follows. When we use the word past, we mean all those events about which we can at least, in principle, know something and obtain some information. Similarly, the word future encompasses all those events that we can at least, in principle, still influence, which we can attempt to change or prevent from occurring. Although it is difficult to explain right away why these definitions of the words past and future should be considered particularly appropriate, it can be easily shown that they actually correspond very closely to the usual use of these expressions. When used in this way, as the results of many experiments show, the area of events referred to as future or past does not depend on the state of motion or other properties of the observer. In more rigorous mathematical language, it can be said that the introduced definition is invariant with respect to the observer's motion. It holds true both in Newtonian mechanics and in Einstein's theory of relativity. However, there is a significant difference here. In classical theory, we assume that the future and the past are separated by an infinitesimal interval of time, which can be called the present and the moment. In the theory of relativity, we see that the situation is somewhat different. The future is separated from the past by a finite interval of time, the duration of which depends on the distance to the observer. Any influence can only propagate at a speed that is less than or equal to the speed of light. Therefore, at a given moment, the observer cannot know or influence events that occurred at some distant point in the interval between two characteristic moments in time. The first moment is the instant when a light signal should be sent from the event's location, which will reach the observer at the time of observation. The second moment is the instant when the light signal sent by the observer at the time of observation reaches the event's location. Indeed, the time interval between these two moments can be called the present for the observer at that moment of observation. Any event occurring in this time interval cannot become known to the observer or experience any influence from the observer at the moment of observation. And this is how the concept of present has been defined. Any event occurring between the two characteristic moments in time can be called simultaneous with the act of observation. The use of the expression can be called already indicates the ambiguity of the word simultaneous, explained by the fact that the word simultaneous originated from everyday experience, within which the speed of light can be considered practically infinitely large. In reality, however, the word simultaneous can be defined in physics somewhat differently. Einstein used this second definition of simultaneity in his works. If two events occur simultaneously at the same point in space, we say that they coincide. This expression is completely unambiguous. Now, Let us imagine 3 points in space lying on a straight line, such that the middle point is equidistant from both endpoints. If 2 events, at both outer points, occur at such moments in time that the light signals sent at the moment of the event arrive at the middle point simultaneously, then both events can be defined as simultaneous. This definition is narrower in this case than the first. One of its most important consequences is that when 2 events are simultaneous for one observer, they may not be simultaneous for another observer. This will occur if the second observer is moving relative to the first. The relationship between the 2 definitions of the word simultaneous can be expressed by the statement: in all cases where 2 events are simultaneous in the first sense, it is also possible to find a reference frame in which they are simultaneous in the second sense. The overall situation can perhaps be illustrated more clearly as follows. Suppose a satellite orbiting the Earth emits a signal that is received by an observation station on Earth after a short interval of time. This observation station, in response to the given signal, sends a command to the satellite, which it receives after a short interval of time. The entire interval of time between sending the signal and receiving the command can be considered on the satellite as simultaneous with the moment of receiving the signal on Earth, according to the first definition. If a specific moment is chosen from this interval on the satellite, then, although this moment is not simultaneous with the moment of receiving the signal on Earth in the sense of the second definition, there always exists a reference frame in which this simultaneity holds. The first definition of the word simultaneous seems somewhat more aligned with the usual use of this word in everyday life, as the question of whether 2 processes are simultaneous in everyday life definitely does not depend on the reference frame. In both relativistic definitions, the concept of simultaneity has acquired a precision that was completely absent in everyday language. In quantum theory, physicists had to realize beforehand that the concept of classical mechanics describes nature insufficiently accurately, that quantum laws limit their applicability, and that therefore great caution is necessary when using them. In the theory of relativity, on the contrary, physicists attempted to change the meaning of the words of classical physics, clarifying these concepts in such a way that they accurately corresponded to the newly discovered situations in nature. The structure of space and time revealed by the theory of relativity manifests itself in many ways across various branches of physics. The electrodynamics of moving bodies can be easily derived from the principle of relativity. This principle itself can be formulated as a very general law of nature that applies not only to electrodynamics or mechanics, but to any group of natural laws. The laws must take the same form in all reference frames that differ from one another only by their state of uniform and straight-line motion. They are invariant, as one could say in mathematical language, with respect to Lorentz transformations. Apparently, the most important consequence of the principle of relativity is the establishment of the property of inertia of energy, or the equivalence of mass and energy. Since the speed of light plays the role of a limiting speed that can never be reached by any material body, it is easy to understand that a moving body must acquire acceleration with more difficulty than a stationary body. Consequently, its energy increases with increasing speed. Generally speaking, every form of energy carries a certain inertia, that is, mass, and the mass corresponding to a given energy is equal to that energy divided by the square of the speed of light. Thus, every form of energy carries mass, but even very large amounts of energy, by ordinary standards, still yield only a very small increase in mass. This is why the mass-energy relationship had not been discovered earlier. The two laws, the law of conservation of mass and the law of conservation of energy, lost their independent validity and became unified into a single law that can be called the law of conservation of energy or mass. When the theory of relativity was developed, the hypothesis of the equivalence of mass and energy revolutionized physics. But at that time, there was very little experimental evidence for this law. Nowadays, one can directly observe in many experiments how elementary particles are born from kinetic energy and how such particles can disappear again, transforming back into energy. Therefore, the conversion of energy into mass and vice versa is no longer unusual. The enormous amounts of energy released during atomic explosions represent another, much more evident proof of the validity of Einstein's relationship. However, it should be noted critically that sometimes it is claimed that the immense energy released during atomic explosions is a direct consequence of the conversion of mass into energy, and that these gigantic amounts of energy could only be predicted based on the theory of relativity. This opinion is based, however, on a misunderstanding. Large amounts of energy stored in atomic nuclei have been known since the time of experiments by Rayleigh, Poynting, and Rutherford. And through radioactive decay, any radioactive substance, such as radium, releases an amount of heat that could be liberated from the same amount of substance in a chemical reaction. The energy released during the decay of uranium nuclei has the same origin as the energy of alpha decay of radium nuclei, namely, primarily the electrostatic repulsion of the two fragments into which the atomic nucleus has split. The energy released during an atomic explosion, therefore, comes directly from this source. It arises from the conversion of mass into energy, as the number of elementary particles with finite rest mass does not decrease at all during an atomic explosion. Indeed, the binding energy of the building blocks of atomic nuclei also manifests itself in the rest masses of the nuclei, and therefore the release of energy is indirectly related to the change in the masses of atomic nuclei. The equivalence of mass and energy, besides its enormous importance for practical physics, has also raised questions related to very old philosophical problems. Various philosophical systems of the past were based on the thesis that substance or matter is indestructible. Experiments conducted in modern physics have shown that elementary particles, such as positrons and electrons, can be destroyed and converted into energy. Does this mean that older philosophical systems are thus refuted by the latest experiences, and that the arguments put forth in these earlier systems should be considered false? This would undoubtedly be somewhat premature and an unjustified conclusion, as the concept of substance and matter in ancient or medieval philosophy cannot simply be equated with the concept of mass in modern physics. If our modern knowledge were expressed in the language of older philosophical systems, one could, for example, consider mass and energy as two different forms of the same substance, thus preserving the notion of the indestructibility of substance. On the other hand, it is hardly possible to say that much is achieved by expressing the latest knowledge in an old language. The philosophical systems of the past were formed from the entire body of knowledge of that time, and therefore correspond to the way of thinking that led to that knowledge. There is every reason to believe that philosophers who contemplated nature many centuries ago could not foresee the development of quantum theory or the theory of relativity. Therefore, the concepts that philosophers of the distant past arrived at through analyzing their knowledge of nature cannot now correspond to phenomena that can only be observed using the most complex technical means of our time. But before discussing the philosophical implications of the theory of relativity, it is necessary to briefly outline its further development. The hypothetical substance ether, which played such an important role in earlier interpretations of Maxwell's theory in the 19th century, as mentioned above, was eliminated by the theory of relativity. This fact is often expressed by stating that absolute space has been eliminated in the theory of relativity. However, such a statement requires some qualifications. Indeed, according to the special theory of relativity, it is no longer possible to choose a specific reference frame relative to which the ether would be at rest and which would therefore deserve the title of absolute. But it would still be incorrect to assert that space has now lost all physical qualities. The equations of motion of material bodies still take different forms in the ordinary reference frame and in another frame that is uniformly rotating relative to the ordinary reference frame. If we limit ourselves to the theory of relativity of 1906, the existence of centrifugal forces in a rotating reference frame proves that there are physical properties of space that allow distinguishing rotating systems from non-rotating ones. In a philosophical sense, this does not seem satisfactory, and it would be preferable to attribute physical properties only to physical objects, such as material bodies or fields, rather than to empty space. However, if we restrict our consideration to electromagnetic processes and mechanical motions, the presence of these properties in empty space follows simply from undeniable facts, such as the existence of centrifugal force. A careful analysis of this situation led Einstein, about a decade later, to a very important generalization of the theory of relativity, commonly referred to as the general theory of relativity. But before proceeding to outline the main ideas of the new theory, it is necessary to say a few words about the degree of reliability that guarantees the validity of these two branches of the theory of relativity. The theory created in 1905 and 1906, that is, the so-called special theory of relativity, is based on a multitude of very precisely verified experimental facts. On the Michelson-Morley experiments and many other similar experiments, on the equivalence of mass and energy in a very large number of radioactive processes, on the very precisely observed dependence of the lifetimes of radioactive objects on the speeds of radioactive particles, and so on. This theory thus serves as a solid, reliable foundation for modern physics and cannot be challenged with our current knowledge. In contrast, the experimental evidence for the general theory of relativity is much less convincing, as the overall experimental material is very limited. There are only a few astronomical observations that can be used to verify the validity of the assumptions of the theory of relativity. Therefore, the second theory is more hypothetical than the first. The crucial, fundamental assumption of the general theory of relativity is the assumption of the equivalence of gravitational and inertial mass. Very careful measurements have shown that the mass of a body, determined by its weight, is precisely proportional to another mass determined by the body's inertia. Even the most accurate measurements have never yielded any deviations from this law. If this law has universal significance, then the force of gravity can be put in parallel with centrifugal or other forces arising as a reaction to inertial effects. Since centrifugal forces must be related to the physical properties of empty space, as shown above, Einstein arrived at the hypothesis that gravitational forces also correspond to the properties of empty space. This was a very important step that immediately necessitated a new step in the same direction. We know that gravitational force is caused by masses, so if gravity is related to the properties of space, then these properties of space must be generated by mass or affected by mass. Centrifugal forces in a rotating reference frame may need to be caused by rotation relative to this frame and very distant masses in the universe. To implement the program outlined in these statements, Einstein needed to connect these fundamental physical considerations with the mathematical framework of general geometry developed by Riemann. Since the properties of space evidently change continuously with variations in gravitational fields, the geometry of the world must resemble the geometry of curved surfaces, in which straight lines of Euclidean geometry must be replaced by geodesics, that is, lines of minimal length whose curvature changes continuously from point to point. As a final result, Einstein was eventually able to propose a mathematical formulation of the relationship between the distribution of masses and the parameters defining geometry. This theory accurately reflects well-known facts characterizing gravity. It is very closely identical to Newton's conventional theory of gravity, and, in addition, predicts some very interesting effects that lie precisely at the limits of the capabilities of measuring instruments. These include, for example, the influence of gravitational force on radiation. If a massive star emits monochromatic radiation, then the light quanta, moving away from the star in a gravitational field, lose part of their energy. It follows that the emitted spectral lines should experience a redshift. So far, as Friedrich has clearly shown, there have been no uncontroversial experimental proofs of the existence of this redshift. However, it would also be premature to conclude that experiments have supposedly refuted the predictions of Einstein's theory. A light ray passing near the sun should be deflected by the sun's gravitational field. This deflection, as has been experimentally shown, is predicted in order of magnitude, but whether the deflection and the precision predicted by Einstein's theory coincide remains an unresolved question. The best experimental evidence for the validity of the general theory of relativity seems to be the precession of the perihelion of the orbit of the planet Mercury, the magnitude of which appears to be in very good agreement with the predictions of the theory. Thus, although the experimental basis of the general theory of relativity is still rather narrow, it nonetheless contains ideas of immense importance. Throughout the development of mathematics, from antiquity to the 19th century, Euclidean geometry was regarded as self-evident. Euclid's axioms pertain to the foundations of any geometric mathematical theory, and represented a basis that could not be called into question. Then, in the 19th century, mathematicians such as Lobachevsky, Gauss, and Riemann found that it was possible to construct other geometries that could be developed with the same mathematical rigor as Euclidean geometry. Therefore, the question of which geometry is true has since become empirical, and only in Einstein's works was this question posed as a physical one. The geometry discussed in the general theory of relativity encompasses not only the geometry of three-dimensional space, but also the four-dimensional manifold of space and time. The theory of relativity establishes a connection between the geometry of this manifold and the distribution of masses in the universe. Thus, this theory raises old questions about space and time in a new form. The case of very large distances suggests answers that can be verified by observations. Consequently, one can once again pose very old philosophical questions that have occupied the human mind since the earliest epochs of philosophy and science. Is space finite or infinite? What was there before the beginning of time? What will happen at the end of time? Or does time have neither a beginning nor an end? These questions have found various answers in different religions and philosophical systems. Aristotle's philosophy, for example, represented all of space in the universe as finite, and although it was infinitely divisible, space arises from the extension of bodies. In a certain sense, it is stretched by bodies. Therefore, where there are no bodies, there is no space. The universe consists of a finite number of bodies: the Earth, the Sun, and the stars. Beyond the sphere of fixed stars, there is no space, so the space of the universe was finite. In Kant's philosophy, this question belonged to what he called antinomy, a multitude of questions that cannot be answered because two different proofs lead to mutually contradictory conclusions. Space cannot be finite because we cannot imagine the end of space, and no matter which point in space we reach, we always imagine that we can move further. But space cannot be infinite either because space is something we can imagine. Otherwise, the concept of space would not arise at all, and we cannot imagine infinite space. Regarding this second assertion, Kant's proofs cannot be conveyed literally. The assertion, space is infinite, means something negative to us. We cannot reach the end of space. For Kant, however, the infinity of space means something real, something that exists in a sense that we can hardly express. Kant concludes that the question of whether space is finite or infinite cannot be answered rationally because the universe as a whole cannot be the subject of our experience. A similar situation arises concerning the problem of the infinity of time. In Augustine's Confessions, for example, the question is posed in the following form: what was God doing before he created the world? Augustine was not satisfied with the well-known answer, God was busy creating. For people asking foolish questions, this would be too cheap an answer, Augustine believes, and he attempts to analyze the problem rationally. Only for us does time flow. We expect it as the future. It passes for us as the present moment, and we remember it as the past. But God is not in time. 1,000 years for him are like one day, and one day is like 1,000 years. Time was created along with the world. It is therefore subject to the world, and thus, at the time when the universe did not exist, there was no time. For God, the entire course of events in the universe was given all at once, meaning there was no time before the world was created by God. Indeed, it is easy to understand that in such formulations, the concept of created immediately leads to significant difficulties. This word, in the way it is usually used, means something that comes into being and did not exist before, and in this sense, it already presupposes the concept of time. Therefore, it is impossible to provide a definition in rational expressions for what can be understood by the phrase, time was created. This circumstance again reminds us of a frequently discussed lesson that must be drawn from the latest developments in physics, namely, that any word or concept, no matter how clear it may seem to us, still has only a limited scope of application. These questions about the infinity of space and time can be posed in the general theory of relativity and, in part, resolved on the basis of empirical material. If the theory correctly describes the connection between the four-dimensional geometry of space and time and the distribution of masses in the universe, then astronomical observations of the distribution of spiral nebulae in space may provide us with information about the geometry of the universe. Then it will be possible to construct at least models of the universe, cosmological pictures, which can be compared with empirical facts. Our modern astronomical knowledge does not allow us to definitively decide which of several possible models should be chosen. It may turn out that the space of the universe is finite, but this would not mean that there is an end to the universe at some point. This would only mean that if we continued to move further and further into the universe in one specific direction, we would eventually have to return to the point from which we started. The situation would thus resemble two-dimensional geometry on the surface of the Earth, where we also, if we move from a certain point further and further, say, in an eastern direction, would eventually return to that point from the west. As for time, it seems that something like a beginning did occur. Many observations indicate that the universe had a beginning about 4 billion years ago, and in any case, that at that time, the matter of the universe was concentrated in a significantly smaller volume of space than it is now, and that since that time, the universe has continued to expand from that small volume at various speeds. This same time of 4 billion years keeps reappearing in many different observations, such as the ages of meteorites, minerals on Earth, and so on. Therefore, it would be difficult to find an explanation for this that is completely different from the idea of the world's emergence 4 billion years ago. If the assumption of emergence in this form turns out to be correct, it will mean that beyond the indicated moment in time, that is, earlier than 4 billion years ago, the concept of time must undergo significant changes. This is more cautious, and the conclusion is placed in the context of a simple formulation about the creation of the world. With the current state of astronomical observations, these questions of the geometry of space-time cannot yet be resolved with any degree of reliability. But it is already quite interesting to know that these questions may later be resolved on a solid foundation of astronomical knowledge. Even if we limit further consideration to the more reliably substantiated special theory of relativity, there is no doubt that this theory has significantly changed our understanding of the structure of space and time. What is perhaps most concerning about these changes is not so much their peculiar nature, but the fact that they were even possible at all. The structure of space and time, which Newton mathematically established as the foundation of his description of nature, contained no internal contradictions, was simple, and corresponded very closely to the concepts of space and time that we are accustomed to in everyday life. The correspondence was so close that Newtonian definitions could be considered merely as precise mathematical formulations of these everyday concepts of space and time. Before the theory of relativity, it was taken for granted that processes could be ordered in time independently of their spatial locations. We know that in everyday life, this impression arises because the speed of light is significantly greater than any other speeds we encounter in daily life. At that time, no one clearly envisioned this limitation. But even now that we know about it, it is hard to imagine that the order of events in time should depend on their spatial arrangement. That is, on the location where they occur. Kant's philosophy later drew attention to the fact that the concepts of space and time are included in our relations with nature. They do not merely belong to nature itself. We cannot describe nature without using these concepts, and therefore, in a certain sense, these concepts are a priori and primarily represent the conditions of experience. They are the result of experience, and thus it is generally assumed that they cannot be altered by new experiences. In light of this, the necessity for changes came as a great surprise. John first felt this necessity when he realized the caution required when attempting to apply the concept of everyday life to experiences refined through the latest experimental techniques. Even the precise and non-contradictory formulation of these concepts in the mathematical language of Newtonian mechanics, or their careful analysis by Kant's philosophy, did not provide any guarantee against the need for critical analysis, which later became possible due to exceptionally accurate measurements. This warning later proved extremely useful for the development of physics, and understanding quantum theory would undoubtedly have been significantly more difficult if the success of the theory of relativity had not warned physicists against the uncritical application of concepts borrowed from everyday life or classical physics. The Copenhagen interpretation of quantum theory has taken physicists far away from the simple materialistic views that dominated the natural sciences of the 19th century, as these views were not only closely tied to the natural sciences of that time, but were also thoroughly analyzed in some philosophical systems, thus deeply penetrating human thought itself. It is entirely understandable that many attempts have been made to critique the Copenhagen interpretation and replace it with another that aligns more closely with the notions of classical physics and materialistic philosophy. These attempts can be categorized into three distinct groups. Representatives of the first group, while fully accepting the Copenhagen interpretation of experiments, at least as it pertains to experiments conducted to date, are dissatisfied with the language used, that is, the philosophical basis underlying it, and seek to replace it with another. In other words, they attempt to change the philosophy without altering the physics. In some works by this first group, agreement with the Copenhagen interpretation is limited to the experimental predictions of this interpretation regarding all experiments that have been conducted thus far, or that pertain only to ordinary electron physics. Representatives of the second group clearly understand that the Copenhagen interpretation is the only acceptable interpretation if experimental data indeed consistently align with the predictions of this interpretation. Therefore, in the works of this group, attempts are made to alter quantum theory at certain points. Finally, representatives of the third group simply express their general dissatisfaction with quantum theory without putting forth specific counterproposals, whether of a physical or philosophical nature. Among the representatives of this group are Einstein, Clapeyron, and Schrödinger. Historically, objections to the Copenhagen interpretation have primarily been raised by this group. All opponents of quantum theory are united, however, in the belief that it would be desirable to return to the classical physics notion of reality, or, to put it more generally in philosophical terms, the ontology of materialism, which posits an objective real world where the smallest parts exist as objectively as stones and trees, regardless of whether they are observed or not. This is impossible, or at least, due to the nature of atomic phenomena, it may not be fully achievable. Our task cannot be to express a wish regarding what atomic phenomena should actually be. Our task can only be to understand them. When examining the works of representatives of the first group, it is important to keep in mind from the outset that the interpretation contained in these works cannot be disproven by experiment, as they merely repeat the Copenhagen Interpretation in a different language. From a positivist perspective, one could even argue that we are not dealing with counter-proposals against the Copenhagen Interpretation, but with their precise repetition in another language, and thus one can only debate the appropriateness of this language. This group of counterproposals employs the idea of hidden parameters, as the laws of quantum theory predict experimental results only statistically. Thus, from a classical point of view, one might assume that there are hidden parameters that, while not observable in any ordinary experiment, actually determine the results of the experiment, as had always been assumed previously, in accordance with the principle of causality. Therefore, in some works, an attempt has been made to invent such parameters within the framework of quantum mechanics. In this regard, for example, Bohm proposed his counter-proposals against the Copenhagen Interpretation, ideas that have recently been somewhat supported by de Broglie. Bohm's interpretation was developed for details, and thus it can serve as a basis for discussion here. Bohm considers particles to be objectively existing structures, akin to material points in classical mechanics. Waves in configuration space are also regarded in his interpretation as objectively existing, similar to electric fields. However, configuration space represents a multidimensional space related to the various coordinates of all particles belonging to the system. In this context, the first difficulty arises. What is meant when waves in configuration space are referred to as really existing? Configuration space is a very abstract space, while the word real comes from the Latin word res, meaning object or thing. But things exist in ordinary three-dimensional space, not in abstract configuration space. Considering waves in configuration space as objective would only be justified if we meant to say that these waves do not depend on the observer. However, they can hardly be called truly existing or real unless we are willing to arbitrarily change the meanings of words. Bohm then defines lines crossing constant phase surfaces at right angles as possible trajectories of particles. Which of these lines will turn out to be the actual trajectory of the particles, according to Bohm, depends on the history of the system and the properties of the measuring device, and this question cannot be resolved without knowledge of the system and measuring device beyond what can actually be known. This history of the system and device effectively contains hidden parameters, namely, the actual trajectory of the electron before the experiment began. One consequence of this interpretation, as Pauli emphasized, is that the electrons of many atoms in a stationary state must be at rest, meaning they should not move in orbits around the atomic nucleus. This seems at first glance to contradict experiments, as measuring the speeds of electrons in the ground state, for example, using the Compton effect, always yields a distribution of ground state electrons by speed, which, according to the rules of quantum mechanics, is given by the square of the wave function in the space of speeds or momenta. In this case, however, Bohm can respond that the measurement is no longer to be considered based on previous laws. Therefore, although the usual assessment of the measurement result as a distribution by speeds would yield the square of the wave function in the space of speeds or momenta. Whether in considering the measuring apparatus, one should take into account quantum theory, and especially in Bohm's view, a priori quantum mechanical potentials, the conclusion that electrons in a stationary state are always at rest would still be permissible. This corresponds to the fact that the quantum potentials introduced by Bohm in this context have very strange properties. For example, they are non-zero at any arbitrarily large distance. At such a price, we hope to assert that there is no need for us to abandon a precise, rational, and objective description of individual systems in the realm of quantum theory. But such an objective description reveals itself as a form of ideological superstructure, only very loosely connected to immediate physical reality, since the hidden parameters in Bohm's interpretation are such that they can never be encountered in the description of real processes, as quantum theory remains unchanged. To avoid this difficulty, Bohm expressed hope that in future experiments, for example, at distances less than 10 to the power of negative 13 centimeters, hidden parameters would still have physical meaning, and thus quantum theory might turn out to be false. Bohr typically remarks regarding such hopeful statements that structurally they are akin to the assertion, one can hope that it will eventually be found that in some cases 2 multiplied by 2 equals 5, as this would be beneficial for our finances. In reality, the fulfillment of Bohm's hopes would undermine not only quantum mechanics, but thus also Bohm's interpretation. Of course, at the same time, it is essential to emphasize that the given analogy, while appearing complete, is not an irrefutable argument against the possible future alteration of Bohm's proposed quantum theory, as it is conceivable that, for instance, the subsequent development of mathematical logic might lend some meaning to the assertion that in exceptional cases 2 multiplied by 2 might equal 5, and that in such cases this generalized mathematics might even be used for calculations in the field of economics. Yet based on facts, without even resorting to convincing logical arguments, we are convinced that such changes in mathematics would not help our finances in any way. Therefore, it is unclear how those mathematical ideas that Bohm points to as possible realizations of his hopes can be applied to describe physical phenomena. If we set aside this possible change in quantum theory, then Bohm's language, as already noted, does not convey anything different regarding physics than the language of the Copenhagen Interpretation. In this case, the only remaining question is the appropriateness of this language. Alongside what we have already noted about the trajectories of particles. When we considered these arguments as unnecessary ideological superstructure, it should also be noted that Bohm's language disrupts the inherent symmetry of quantum theory between coordinates and velocities, or more precisely, coordinates and momenta. Since the properties of symmetry always pertain to the profound physical essence of the theory, it remains unclear what we gain by eliminating them in the corresponding language. A similar objection, albeit in a slightly different form, can be raised against Bohm's statistical interpretation, which is somewhat distinct from its interpretation. Nevertheless, Bohm accepts the emergence and annihilation of particles as the fundamental quantum mechanical process, which are real in the classical sense of the word, namely in the sense of materialistic ontology, and the laws of quantum mechanics are viewed as a special case of correlation statistics, which is here applied to the processes of emergence and annihilation of particles. Such an interpretation can be conducted, as Bohm has shown, without contradictions, and it sheds light on interesting connections between quantum theory and correlation statistics. From a physical standpoint, it leads to the same conclusions as the Copenhagen interpretation. In a positivist sense, it is therefore again due to this interpretation, just as with Bohm's interpretation. However, its language violates the symmetry of waves and particles, which is a particularly characteristic feature of the mathematical framework of quantum theory. As early as 1928, Jordan, Klein, and Wiener demonstrated that this mathematical framework can be interpreted not only as quantization of particle motion, but also as quantization of three-dimensional material waves. Therefore, there are no grounds to consider matter waves less real than particles. The symmetry of waves and particles could perhaps be preserved in Bohm's interpretation if the corresponding correlation statistics were developed and applied to material waves in space and time. And if this were the case, it could leave the question open as to whether particles or waves should be considered the true reality. The assumption of the real existence of particles in the sense of materialistic ontology necessarily leads to attempts to believe that, at least in principle, deviations from the uncertainty relations are possible. For example, Finnish argues that the existence of the uncertainty relation, which he also links to certain statistical relations, in no way excludes the possibility of simultaneous and arbitrarily precise measurement of coordinates and velocity. However, Finnish does not specify how such measurements should practically appear, and therefore his considerations seem to remain abstract and mathematical. After all, either the propositions that are related to those of Bohm and Finnish link the sought hidden parameters with a new, invented for this purpose, type of particles called zero, which cannot be observed in any way. Such a notion carries the danger that the interaction of real particles with drones will lead to the scattering of energy across a large number of degrees of freedom of these drones, turning all thermodynamics into chaos. Bohm did not explain how he could overcome this danger. The perspective from which all groups of physicists critiquing the Copenhagen interpretation have approached the issue can best be characterized by recalling the discussion surrounding the special theory of relativity. Those who were dissatisfied with Einstein's elimination of absolute space and absolute time could argue as follows. The special theory of relativity has not proven that there is absolutely neither space nor absolute time. It has only shown that true space and true time do not manifest themselves in all ordinary experiments. But if the relevant laws of nature are properly accounted for, and thus the correct apparent times are introduced for the moving coordinate system, nothing would contradict the assumption of absolute space. It would even be plausible to assume that the center of mass of our galaxy, at least approximately, is at rest in absolute space. A critic of the special theory of relativity could further add that one can hope that future measurements will make the definition of absolute space, so to speak, a hidden parameter of the theory of relativity possible, thus disproving the theory of relativity. This argumentation cannot, as is immediately evident, be experimentally disproven, as no claims are made that differ from those of the special theory of relativity. However, such an interpretation of the theory of relativity would violate, at least in the language applied, precisely the most important properties of symmetry of the theory of relativity, namely invariance under Lorentz transformations, and therefore it should be considered unacceptable. The analogy between the discussion of the special theory of relativity and the discussions of quantum theory is evident. The laws of quantum mechanics are such that hidden parameters introduced specifically for this purpose can never be observed. Moreover, the most important properties of symmetry would be violated if we introduced hidden parameters into the interpretation of the theory as fictitious quantities. The objections contained in the works of Blokhintsev and Alexandrov are fundamentally different in their formulation from those discussed above. These objections are initially limited exclusively to the philosophical aspect of the question. Physically, Blokhintsev and Alexandrov unreservedly agree with the Copenhagen interpretation. The external forms of their polemics are all the more striking. Quoting, "Among the most diverse idealistic currents in modern physics, the so-called Copenhagen school is the most reactionary." This article is dedicated to the exposure of the idealistic and Gnostic speculations of this school surrounding the fundamental problems of quantum mechanics, writes Blokhintsev in the introduction to one of his articles. The sharpness of the polemic indicates that this discussion is not only about science, but also about belief. The aim of the critique is expressed in the conclusion of the article with a quote from Lenin's writings. As strange as it may seem from the standpoint of common sense, the transformation of weightless ether into weighty matter and back, as strange as the absence of any mass in the electron other than electromagnetic mass, as unusual as the limitation of mechanical laws of motion to only one area of natural phenomena, and their subjugation to deeper laws of electromagnetic phenomena, and so on. All this is merely further confirmation of dialectical materialism. End of quote. Although, therefore, the premises of the works of Blokhintsev and Alexandrov lie outside the realm of natural science, the discussion of their arguments is quite instructive. In this case, the main task is to save materialistic ontology, and therefore the introduction of the observer into the interpretation of quantum theory is primarily attacked. Alexandrov writes, "Therefore, the results of quantum mechanics measurements should be understood as the objective effect of the interaction of the electron with the appropriate object. Talks about the observer should be excluded when dealing with objective conditions and objective effects. A physical quantity is an objective characteristic of a phenomenon, not a result of observation. The wave function characterizes, according to Alexandrov, the objective state of the electron." In his exposition, Alexandrov overlooks that the interaction of the system with the measuring device, if the measuring instruments of the system are considered isolated from the rest of the world and are generally examined according to quantum mechanics, usually does not lead to a definite result. For example, to the exposure of the photoplate at a specific point when an electron hits it in a double-slit experiment. When it is asserted against these conclusions that in reality the plate will still show the object at a specific location after the interaction, then the quantum mechanical consideration of the isolated system consisting of the electron and the plate is abandoned. This reflects the factual nature of the event, which can be described using everyday concepts, but is not directly contained in the mathematical formalism of quantum theory, and enters the Copenhagen interpretation through the introduction of the notion of the observer. Of course, the introduction of the observer should not be misunderstood as introducing some subjective traits into the description of nature. The observer performs rather the function of a classical recording device, that is, registering processes in space and time, and it does not matter whether the observer is a machine or a living being. The registration, that is, the transition from possible to actual, is in this case undoubtedly necessary and cannot be excluded from the interpretation of quantum theory. In this regard, quantum theory is closely linked to thermodynamics, as every active observation is inherently an irreversible process. Only through such irreversible processes can the formalism of quantum theory be coherently connected to actual processes in space and time. On the other hand, irreversibility, if translated back into the language of mathematical representation of events, is a consequence of the incompleteness of knowledge that the observer has about the system, and therefore is not entirely something objective. The formulations of Blokhintsev are somewhat different from those of Alexandrov. In quantum mechanics, the states of a particle are characterized not by themselves, but by the particles belonging to a certain ensemble, whether mixed or pure. This belonging has a completely objective character and does not depend on the observer's opinion. End of quote. Such formulations actually lead us very far, even too far, from the ontology of materialism. The point is that, for example, in classical thermodynamics, when determining the temperature of a system, the observer implies that the system represents only one sample chosen from a canonical ensemble, and thus he can consider that the system presumably possesses various energies. However, in reality, the system in classical physics at a given moment in time has only a specific value of energy, and all other values are not realized. The observer, therefore, would fall into error if he were to assume that at that moment another value of energy exists. Thus, the canonical ensemble contains a statement not only about the system itself, but also about the incompleteness of the observer's information about the system. When Blokhintsev tries to regard the belonging of a system to an ensemble in quantum theory as something completely objective, he uses the word objective in a sense that differs from its use in classical physics, as in the latter, this belonging signifies not only a statement about the system, but also about the degree of knowledge of the observer about the system. In considering quantum theory, it is necessary to briefly mention one exception. If the ensemble is characterized in quantum theory solely by a single wave function in configuration space, rather than, as usual, by a statistical matrix, a special situation arises, known as a pure case, in which the description can be termed objective in a certain sense, and in which the element of incomplete knowledge is not directly revealed. However, since every measurement, due to the irreversible processes associated with it, again introduces an element of incomplete knowledge, this situation of the pure case does not fundamentally differ from the previously condemned more general case. From all that has been discussed above, it is primarily evident how difficult it is to fit new ideas into an old system of concepts that precedes philosophy, or, using an old expression, how challenging it is to put new wine into old wineskins. Such attempts are always unpleasant because they force one to repeatedly patch the inevitable holes in the old wineskins instead of enjoying the new wine. From the standpoint of common sense, one cannot expect that thinkers who created dialectical materialism more than 100 years ago could foresee the development of quantum theory. Their notions of matter and reality cannot be adapted to the results of our today's refined experimental techniques. Here, perhaps, a few additional remarks about the position of the natural scientist regarding a specific worldview should be made. It does not matter whether the discussion pertains to a religious or political worldview. The fundamental difference between religious and political worldviews is that the latter relates to the immediate material reality of the world around us, while the former concerns another reality that lies beyond the material world. In this formulation of the problem, it is inconsequential. Here, the problem of belief itself should be discussed. From what has been said so far, it follows that a scientist should never rely on any single doctrine, nor should he limit the methods of his thinking to one single philosophy. A scientist must be prepared for the possibility that new experimental data may change even the very foundations of his knowledge. However, this requirement, for two reasons, would again represent too great a simplification of our situation in life. The first reason is that the entire framework of our thinking is shaped in our youth by the ideas we encounter at that time, or by the contact we have with outstanding individuals from whom we learn. This framework will decisively influence all our subsequent work, and as a result, it is entirely possible to encounter difficulties in adapting to entirely different ideas and systems of thought. The second reason is that we always belong to some society or community. This community is united by common ideas, a shared criterion of moral values, or a common language used to discuss universal problems of life. These common ideas may be supported by the authority of the church, party, or state, and even if this is not the case, it is still very difficult to deviate from accepted ideas without opposing oneself to society. However, the results of scientific reflections may contradict some of the commonly accepted ideas. Undoubtedly, it would be unreasonable to demand that scientists not be loyal members of society, that they fundamentally renounce all the benefits that can be gained from belonging to a collective. And it would be equally unreasonable to wish that the common ideas of a collective or society, which from a scientific perspective are always a necessary simplification, should be changed immediately following each success of scientific knowledge. Therefore, even in our time, we return to the old problem of the duality of truth, which has repeatedly arisen in the history of Christian religion during the late Middle Ages. At that time, a highly contentious doctrine emerged, asserting that positive religion, regardless of the form it may take, is a necessity for the vast majority of people, while the scientist seeks the truth beyond religion and can find it only there. Science is an esoteric teaching, it was said, intended only for the few. In our time, the functions of positive religion in some countries have been assumed by political doctrines and social organizations, but the essence of the problem remains the same. The first requirement concerning a scientist must always be the demand for intellectual honesty. While society will often ask the scientist, due to the variability of science, to wait at least several decades before publicly expressing his views that diverge from the commonly accepted opinion. There is probably no simple solution to this problem, especially if tolerance is insufficient. But perhaps one can find some solace in the fact that this undoubtedly concerns fairly old problems related to human life at all times. Now let us return to the counter-proposals of the Copenhagen interpretation of quantum theory and examine the counter-proposals of representatives of the second group. In these counter-proposals, the attempt to construct an alternative philosophical interpretation is even linked to the desire to change quantum theory itself. A conscientious attempt in this direction has been made by Yanasi, who realized that the assumption of the strict validity of quantum mechanics compels us to depart from the notions of reality in classical physics. He therefore attempts to modify quantum mechanics in such a way that many of its results remain valid while its structure approaches that of classical physics. The direction of his attack is the so-called wave packet reduction. That is, the fact that the wave function describing the system changes abruptly at the moment when the observer becomes aware of the result of the observation. Yanasi states that this reduction cannot be derived from Schrödinger's equation, and believes that this allows for a conclusion about the inconsistency of the orthodox interpretation. As is known, wave packet reduction appears in the Copenhagen Interpretation always in those cases, in the language of formalism, always for statistical mixtures of states, when the transition from possible to actual is completed, that is, when something is actually chosen from the possible, which, according to the usual description, is done by the observer. This is based on the assumption that interference terms are partially suppressed due to uncontrolled interactions between the measuring device of the system and the rest of the world, which prepares a mixture. Yanasi attempts to modify quantum mechanics in this point by introducing damping, so that the interference terms would disappear by themselves after a finite time. Even if this were true, all the experiments conducted to date provide no grounds for this. Thus, in such an interpretation, as Yanasi himself notes, a number of undesirable consequences would remain, such as waves propagating faster than the speed of light, changing the temporal sequence of cause and effect for a moving observer, that is, the highlighting of certain reference systems, and so on. Therefore, we are unlikely to agree to sacrifice the simplicity of quantum theory for such ideas unless compelled to do so by experiment. Among other opponents of the orthodox interpretation of quantum theory, Schrödinger occupies a unique position in a certain sense, as he would like to attribute objective reality not to particles, but to waves, and he disagrees with interpreting waves merely as waves of probability. In his work, Do Quantum Jumps Exist?, he attempts to entirely reject quantum jumps, but Schrödinger's work primarily contains a misunderstanding of the conventional interpretation. He overlooks the fact that in the conventional interpretation, only the waves in configuration space are waves of probability, which can be mathematically described as transformation matrices. They are three-dimensional waves of matter or radiation. The latter are objectively real to the same extent as particles. Although they are not directly related to waves of probability, they possess similar axioms of continuous energy and momentum density. Of course, Schrödinger rightly emphasizes that these processes can be considered more continuous than is typically done in most cases. However, Schrödinger cannot eliminate from the world the element of discontinuity that is found everywhere in atomic physics, for example, very clearly on a scintillation screen. In the conventional interpretation of quantum theory, this element is contained in the transition from possible to actual. Schrödinger himself does not make any counter-proposals regarding how he envisions the introduction of a universally observable element of discontinuity, other than what is done in the conventional interpretation. Finally, the criticism found in various works by Einstein and others focuses on the question of whether the Copenhagen interpretation allows for an unambiguous objective description of physical facts. The most important arguments can be expressed as follows. The mathematical framework of quantum theory seems to provide a sufficient description of the statistics of atomic phenomena. But even if its assertions regarding the probabilities of atomic processes are entirely correct, this interpretation still does not provide any description of what actually happens independently of observations. Something must indeed be happening between our observations. Of that we can be certain. This something may not be describable using the concepts of an electron, wave, or light quantum. But since it is not described in any way, the task of physics remains unfulfilled. It cannot be accepted that quantum physics pertains only to observation. A physicist must assume in their science that they are studying a world that they did not create, and that would exist in essentially the same way without them. Therefore, the Copenhagen Interpretation does not provide any genuine understanding of atomic processes. It is easy to see that this criticism simply calls for a return to the old materialist ontology. What can be said in response to this criticism? From the perspective of the Copenhagen Interpretation, it can be stated that physics is a part of natural science, and, as such, should strive to describe and understand nature. However, any kind of understanding, whether scientific or not, depends on our language, on how we can convey our thoughts, and what exactly we convey. Any description of phenomena, experiments, and their results is also based on language as the sole means of understanding. The words of this language express concepts from everyday life, which can be refined in the scientific language of physics to the concepts of classical physics. These concepts represent the only means of unambiguous communication about processes, the arrangement of instruments in experiments, and their results. Therefore, when physics is asked to provide a description of what is actually happening in its experiments, the words description, reality, and happening can only relate to concepts from everyday life, that is, classical physics. As soon as a physicist attempts to abandon this foundation, they would lose the ability to communicate unambiguously and would be unable to advance their science further. Thus, any statement about what is actually happening or has happened is a statement that uses the concept of classical physics. By its very nature, it is incomplete regarding the details of atomic processes that are being discussed here due to the laws of thermodynamics and the uncertainty principle. The demand that one should describe what happens in a quantum mechanical process. In the interval between two successive observations is a contradiction and a conflict between the defined word and the definition. The Latin quad of the word describe relates only to the application of classical concepts, whereas these concepts cannot be applied in the intervals between two observations. They can only be applied at the moment of observation. It should also be emphasized that the Copenhagen interpretation of quantum theory is in no way positivist. While positivism is based on sensory perceptions of elements of existence, the Copenhagen interpretation considers objects and processes described in classical terms, that is, the actual, as the foundation of any physical explanation. At the same time, it is also recognized that statistically, the nature of the laws of microphysics cannot eliminate this, as any knowledge of the actual, according to quantum mechanical laws of nature, is incomplete knowledge. The ontology of materialism was based on the illusion that the realm of the intelligent could be extrapolated from the way the directly given surrounding world exists, but this extrapolation is impossible. Additional remarks could be made regarding the formal structure of counter-proposals concerning the Copenhagen Interpretation. All counter-proposals put forth so far regarding the Copenhagen Interpretation require sacrificing essential properties of symmetry in quantum theory. Therefore, it can be reasonably assumed that the Copenhagen Interpretation is necessary if these symmetry properties, similar to the property of invariance under Lorentz transformations, are considered essential properties of nature. This is also supported by all experiments conducted so far. The concept of matter has undergone changes throughout the history of human thought in various philosophical systems and has been interpreted in different ways. When we use the word matter, we must keep in mind that the various meanings attributed to the concept of matter have, to a greater or lesser extent, persisted in modern science. Early Greek philosophy, from Thales to Aristotle, sought a single principle in the infinite change of all things and formulated the concept of cosmic matter, a world substance undergoing all these changes, from which all individual things arise and into which they ultimately transform again. This matter was partially identified with a specific substance, water, air, or fire, while partially it was not attributed any other qualities beyond those of the material from which all objects are made. Later, the concept of matter played an important role in Aristotle's philosophy in his ideas about the connection between form and matter and form and substance. Everything we observe in the world is a phenomenon that represents formed matter. Matter, therefore, is not reality in itself, but represents only possibility, potential. It exists only through form in the phenomena of nature. Being, as Aristotle calls it, transitions from possibilities to actuality, to what has been actualized through form. Matter in Aristotle's view is not any specific substance, such as water or air, nor is it empty space. It turns out to be, to some extent, an indeterminate corporeal substrate that contains the possibility of transitioning through form into what has been actualized. A typical example of this relationship between matter and form in Aristotle's philosophy is biological development, where matter transforms into living organisms, as well as the creation of a work of art by a human. One could say that the living statue is potentially contained in the marble even before the sculptor chisels it out. Only significantly later, starting with Descartes' philosophy, was matter as something primary opposed to spirit. There are two complementary aspects of the world, matter and spirit, or, as Descartes expressed it, res extensa and cogito. Since the new methodological principles of natural science, especially mechanics, excluded the reduction of corporeal phenomena to spiritual forces, matter could be regarded only as a special reality, independent of the human spirit and any supernatural forces. Matter during this period is presented as already formed matter, and the process of formation is explained by a causal chain of mechanical interactions. Matter has already lost its connection with the vegetative soul of Aristotelian philosophy, and therefore the dualism between matter and form no longer plays any role at this time. This conception of matter has made the greatest contribution to what we now understand by the word matter. Finally, in the natural sciences of the 19th century, another dualism played an important role, namely, the distinction between matter and force, or, as it was then said, between force and substance. Forces can act on matter, and matter can give rise to forces. Matter, for example, generates gravitational force, and this force, in turn, acts on it. Force and substance are thus two clearly distinguishable aspects of the physical world. Since forces are also formative forces, this distinction again approaches Aristotle's differentiation between matter and form. On the other hand, precisely in connection with the latest developments in modern physics, this distinction between force and substance completely disappears, as every force field contains energy and, in this respect, also represents part of matter. Each force field corresponds to a certain type of elementary particles. Particles and force fields are merely two different forms of manifestation of the same reality. When natural science studies the problem of matter, it should primarily investigate the forms of matter. The infinite variety of the variability of forms of matter should become the immediate object of research. Efforts should be directed toward finding the laws of nature, unified principles that could serve as a guiding thread in this infinite field of research. Therefore, just as natural science, and especially physics, has long focused its interests on analyzing the structure of matter and the forces that determine this structure. Since the time of Galileo, the primary method of natural science has been experimentation. This method has made it possible to transition from general studies of nature to specific investigations, to isolate characteristic processes in nature, based on which its laws can be studied more directly than in general studies. That is, in studying the structure of matter, it is necessary to conduct experiments on them, to place matter under unusual conditions, to study its transformation in those circumstances. I hope to thereby understand certain fundamental features of matter that persist through all its visible changes. Since the formation of modern natural science, this has been one of the most important goals of chemistry, which quite early arrived at the concept of a chemical element, a substance that could not be further decomposed or split by any means available to chemists at the time. Boiling, burning, dissolving, mixing with other substances. It was called an element. The introduction of this concept was the first crucial step in understanding the structure of matter. The diversity of substances found in nature was thus reduced, at least, to a comparatively small number of simpler substances, elements. And because of this, a certain order was established among the various phenomena of chemistry. The word atom was therefore applied to the smallest unit of matter that makes up a chemical element, and the smallest particle of a chemical compound could be visually represented as a small group of different atoms. The smallest particles of the element iron turned out to be, for example, iron atoms, while the smallest particle of water, the so-called water molecule, was found to consist of one oxygen atom and two hydrogen atoms. The next and almost equally important step was the discovery of the conservation of mass in chemical processes. If, for example, carbon is burned and carbon dioxide is formed, then the mass of the carbon dioxide equals the sum of the masses of carbon and oxygen before the process began. This discovery gave the concept of matter primarily a quantitative meaning, independent of chemical properties. Matter could be measured and quantified by its mass. During the next period, primarily in the 19th century, a large number of new chemical elements were discovered. In our time, their number has surpassed 100. However, this number clearly indicates that the concept of a chemical element has not yet led us to the point from which we could understand the unity of matter. The assumption that there are many qualitatively different types of matter, between which there are no internal connections, was unsatisfactory. By the beginning of the 20th century, evidence had already been found in favor of the existence of interconnections between various chemical elements. This evidence consisted in the fact that the atomic weights of many elements appeared to be whole number multiples of some smallest and genetic weight, which approximately corresponds to the atomic weight of hydrogen. The similarity of the chemical properties of certain elements also indicated the existence of this interconnection. But only through the application of forces that are many times stronger than those acting in chemical processes could the connection between different elements truly be established and approach an understanding of the unity of matter. The attention of physicists was drawn to these forces with the discovery of radioactive decay, accomplished by Becquerel in 1896. Subsequent research by Curie, Rutherford, and others into the transformations of elements in radioactive processes clearly demonstrated that alpha particles are emitted in these processes as fragments of atoms with energy that is approximately 1,000,000 times greater than the energy of a single particle in a chemical process. Thus, these particles could now be used as a new tool for investigating the internal structure of the atom. The nuclear model of the atom, proposed by Rutherford in 1911, was the result of experiments on the scattering of alpha particles. The most important feature of this well-known model was the separation of the atom into two completely different parts, the atomic nucleus and the surrounding electron shells. The atomic nucleus occupies only an exceptionally small portion of the entire space that the atom occupies. The radius of the nucleus is approximately 100,000 times smaller than the radius of the entire atom, yet it contains almost the entire mass of the atom. Its positive electric charge, which is an integer multiple of the so-called elementary charge, determines the total number of electrons surrounding the nucleus. The atom, as a whole, must be electrically neutral, thus determining the shape of the electron trajectories. This distinction between the atomic nucleus and the electron shell immediately provided a coherent explanation for the fact that in chemistry, it is precisely chemical elements that are the ultimate units of matter, and that very large forces are necessary for the transformation of elements into one another. Chemical bonds between neighboring atoms are explained by the interaction of electron shells and the energy of interaction. In this case, relatively small electrons, accelerated in a discharge tube by a potential of only a few volts, possess sufficient energy to loosen the electron shells and cause the emission of light or break the chemical bond in a molecule. However, the chemical behavior of the atom, although fundamentally based on the behavior of electron shells, is determined by the electric charge of the atomic nucleus. If one wishes to change the chemical properties, the atomic nucleus itself must be altered, which requires energies that are approximately 1,000,000 times greater than those present in chemical processes. However, the nuclear model of the atom, viewed as a system in which the laws of Newtonian mechanics are fulfilled, cannot explain the stability of the atom. Only the application of quantum theory to this model can explain the fact that, for example, a carbon atom, after interacting with other atoms or emitting a quantum of light, still remains ultimately a carbon atom with the same electron shell it had previously. This stability can be simply explained based on those very features of quantum theory that make possible an objective description of the atom in space and time. Thus, an initial foundation was created for understanding the structure of matter. The chemical and other properties of atoms could be explained by applying the mathematical framework of quantum theory to electron shells. From this foundation, one could then attempt to introduce an analysis of the structure of matter in two different directions. One could either study the interactions of atoms, their relationship to larger units such as molecules or crystals, or biological objects, or one could attempt, by investigating atomic nuclei and their constituent parts, to advance to the point where the unity of matter would become understandable. Physical research has been rapidly developing in both directions over the past decades. The following exposition will be dedicated to clarifying the role of quantum theory in both of these areas. The forces between neighboring atoms are primarily electrical forces. We are talking about the attraction of opposite charges and the repulsion between like charges. Electrons are attracted to the atomic nucleus and repelled by other electrons. However, these forces do not act according to the laws of Newtonian mechanics, but according to the laws of quantum mechanics. This leads to two different types of bonding between atoms. In one type of bond, the electron of one atom transfers to another atom, for example, to fill a not yet fully occupied electron shell. In this case, both atoms ultimately become electrically charged and are referred to as ions, since their charges are then opposite, causing them to attract each other. The chemist refers to this as polar bonding. In the second type of bond, the electron, in a manner characteristic only to quantum theory, belongs to both atoms. If we use the picture of electron orbits, we can roughly say that the electron orbits around both atomic nuclei and spends a significant portion of its time in both atoms. This second type of bond corresponds to what the chemist calls covalent bonding. These two types of bonds, which can exist in all possible combinations, ultimately lead to the formation of various aggregates of atoms and ultimately determine all the complex structures studied by physics and chemistry. Thus, chemical compounds are formed because atoms of different kinds create small closed groups, and each group can be called a molecule of a chemical compound. When forming crystals, atoms are arranged in ordered lattices. Metals are formed when atoms are packed so tightly that the outer electrons leave their shells and can move through the entire piece of metal. The magnetism of certain substances, especially some metals, arises due to the rotational motion of individual electrons within the metal, and so on. In all these cases, the dualism between matter and force can still be preserved, as electrons can be viewed as the building blocks of matter held together by electromagnetic forces. While physics and chemistry, where they relate to the structure of matter, constitute a unified science. In biology, with its more complex structures, the situation is somewhat different. Indeed, despite the striking integrity of living organisms, a sharp distinction between living and non-living matter cannot likely be drawn. The development of biology has provided us with numerous examples demonstrating that specifically biological functions can be performed by special large molecules or groups or chains of such molecules. These examples emphasize a tendency in modern biology to explain biological processes as consequences of the laws of physics and chemistry. However, the stability we observe in living organisms is somewhat different in nature from the stability of an atom or a crystal. In biology, it is more about the stability of a process or function than about the stability of form. Undoubtedly, quantum mechanical laws play a very important role in biological processes. For example, in understanding large organic molecules and their diverse geometric configurations. Essential specific quantum mechanical forces, which can only be somewhat inaccurately described based on the concept of chemical valency. Experiments on biological mutations induced by radiation also demonstrate both the importance of the statistical nature of quantum mechanical laws and the existence of amplification mechanisms. The close analogy between processes in our nervous system and processes occurring in the functioning of modern electronic counting machines again emphasizes the importance of individual elementary processes for living organisms. However, all these examples do not prove that physics and chemistry, supplemented by teachings and developments, will enable a complete description of living organisms. Biological processes must be treated naturally by testers and experimenters with greater caution than processes in physics and chemistry. As Bohr explained, it may well turn out that the description of a living organism, which from a physicist's perspective could be called complete, does not exist at all, because such a description would require experiments that would come into too strong conflict with the biological functions of the organism. Bohr described this situation as follows. In biology, we are dealing more with the realization of possibilities in that part of nature to which we belong than with the results of experiments that we can produce ourselves. The situation of complementarity in which this formulation is effectively reflected manifests as a tendency in the methods of modern biology. On the one hand, fully utilizing the methods and results of physics and chemistry, and on the other hand, still constantly employing concepts that pertain to those features of organic nature that are not contained in physics and chemistry, such as the very concepts of life itself. Thus, we have conducted an analysis of the structure of matter in one direction, from the atom to more complex structures composed of atoms, from atomic physics and solid-state physics to chemistry, and finally to biology. Now, we must turn in the opposite direction and trace the line of research directed from the external realms of the atom to the internal realms, to the atomic nucleus, and finally to elementary particles. Only this second line may lead us to an understanding of the unity of matter. Here, there is no need to fear that the characteristic structures will be destroyed in experiments. If the task is to test experimentally the fundamental unity of matter, we can subject matter to the strongest possible forces, to the most extreme conditions, to see if ultimately matter can be transformed into some other matter. The first step in this direction was the experimental analysis of the atomic nucleus. In the early periods of these studies, which filled approximately the first 3 decades of our century, the only tool for experiments on the atomic nucleus was alpha particles emitted by radioactive substances. With these particles, Rutherford was able, in 1919, to transform the atomic nuclei of light elements into one another. He was able, for example, to transform a nitrogen nucleus into an oxygen nucleus by adding an alpha particle to the nitrogen nucleus while simultaneously knocking out a proton from it. This was the first example of a process at distances on the order of atomic nucleus radii, reminiscent of chemical processes, leading to the artificial transformation of elements. The next decisive success was the artificial acceleration of protons in high-voltage devices to energies sufficient for nuclear transformations. For this purpose, voltage differences of approximately 1 million volts are required, and both Rose and Walt succeeded in their first decisive experiment in transforming the atomic nuclei of lithium into the atomic nuclei of helium. This discovery revealed to researchers an entirely new field that can be called nuclear physics in the strict sense of the term, and which quickly led to a qualitative understanding of the structure of the atomic nucleus. In fact, the structure of the atomic nucleus turned out to be very simple. The atomic nucleus consists of only two different types of elementary particles. One of the elementary particles, the proton, is simultaneously the nucleus of hydrogen. The other was named the neutron, a particle that has approximately the same mass as the proton, and is, moreover, electrically neutral. Each atomic nucleus can thus be characterized by the total number of protons and neutrons of which it consists. The nucleus of a normal carbon atom consists of 6 protons and 6 neutrons, but there are also other nuclei of carbon atoms that are somewhat rarer. They have been called isotopes, the first of which consists of 6 protons and 7 neutrons, and so on. Thus, in the end, we arrived at a description of matter in which instead of many different chemical elements, only 3 basic units were used, 3 fundamental building blocks: proton, neutron, and electron. All matter consists of atoms, and is therefore ultimately built from these 3 basic building blocks. This does not yet mean the unity of matter, but it undoubtedly represents an important step toward that unity, and perhaps even more importantly, signifies a substantial simplification. However, there was still a long way to go from knowing these basic building blocks of the atomic nucleus to fully understanding its structure. Here, the problem was somewhat different from the corresponding problem regarding the outer shell of the atom, which was resolved in the mid-20s. In the case of the electron shell, the forces between particles were known with great precision, but in addition, dynamic laws had to be found, and they were ultimately formulated in quantum mechanics. In the case of the atomic nucleus, it could be fully assumed that the dynamic laws are primarily the laws of quantum theory. But here, there were, above all, unknown forces between particles that needed to be derived from the experimental properties of atomic nuclei. This problem has not yet been completely resolved. The forces are likely not as simple as in the case of electrostatic forces between electrons in the outer shells, and therefore mathematically deriving the properties of atomic nuclei from more complex forces is more challenging. Furthermore, progress is hindered by the inaccuracy of experiments, but qualitative representations of the structure of the nucleus have acquired a quite definite form. Ultimately, the last major problem remains the problem of the unity of matter. Are these elementary particles, proton, neutron, and electron, the final indivisible building blocks of matter, in other words, atoms, the meaning of which in Democritus's philosophy is that they have no mutual connections, abstracting from the forces acting between them, or are they merely different forms of the same type of matter? Furthermore, can they transform into one another, or even into other forms of matter? To experimentally resolve this problem, forces and concentrated energies on atomic particles are required that must be many times greater than those used to investigate the atomic nucleus. Since the energy reserves in atomic nuclei are not sufficiently large to provide us with the means to conduct such experiments, physicists must either utilize forces in space, that is, in the space between stars, on the surfaces of stars, or they must rely on the skills of engineers. In fact, successes have been achieved on both paths. First and foremost, physicists have utilized what is known as cosmic radiation. Electromagnetic fields on the surfaces of stars, extending over gigantic distances, under favorable conditions, can accelerate charged atomic particles, electrons, and atomic nuclei, which, due to their greater inertia, have more opportunities to remain in the accelerating field for a longer time. And when they finally leave the surface of a star into empty space, they sometimes manage to traverse potential fields of billions of volts. Further acceleration under favorable conditions occurs still in the variable magnetic fields between stars. In any case, it turns out that atomic nuclei are held for a long time by variable magnetic fields in the space of the galaxy. Ultimately, they thus fill the space of the galaxy with what is called cosmic radiation. This radiation reaches Earth and thus consists of all possible atomic nuclei of hydrogen, protein, and heavier elements, the energies of which vary from hundreds or thousands of millions of electron volts to amounts a million times greater. When particles of this high-altitude radiation penetrate the upper layers of the Earth's atmosphere, they collide with nitrogen or oxygen atoms in the atmosphere, or with atoms of any experimental device subjected to cosmic radiation. The results of this interaction can then be investigated. Another possibility is the construction of very large accelerators of elementary particles. The so-called cyclotron, which was constructed in California in the early 30s by Lorentz, can be considered a prototype for them. The basic idea of the design of these installations is that, due to a strong magnetic field, charged atomic particles are forced to rotate in circles multiple times so that, on this circular path, they can be repeatedly accelerated by the electric field of the installation, where energies of several hundreds of millions of electron volts can be achieved. Currently, such installations operate in many places around the world, primarily in the United Kingdom. Thanks to the collaboration of 12 European countries, a very large accelerator of this kind is being built in Geneva, which is hoped to produce protons with energies of up to 25 million electron volts. Experiments conducted using cosmic radiation and very large accelerators have revealed new and interesting features of matter. In addition to the three fundamental building blocks of matter, the electron, proton, and neutron, new elementary particles have been discovered, which are generated in high-energy collisions and disappear after extremely short intervals of time, transforming into other elementary particles. The new elementary particles have properties similar to those of the old ones, except for their instability. Even the most stable among the new elementary particles have a lifespan of only about 1/1,000,000th of a second, while the lifetimes of others are hundreds or thousands of times shorter. Currently, approximately 25 different types of elementary particles are known, the youngest of which is the negatively charged proton, known as the antiproton. At first glance, these results seem to diverge from the idea of the unity of matter, as the number of fundamental building blocks of matter appears to have increased again to a quantity comparable to that of various chemical elements. However, this would be an inaccurate interpretation of the actual state of affairs, as experiments have simultaneously shown that particles arise from other particles and can be transformed into other particles, that they are formed simply from the kinetic energy of such particles and can disappear again, leading to the emergence of other particles. Thus, in other words, experiments have demonstrated a complete transformation of matter. All elementary particles in sufficiently high energy collisions, can transform into other particles, or can simply be created from kinetic energy, and they can convert into energy, for example, into radiation. Therefore, we actually have definitive proof of the unity of matter. All elementary particles are made, so to speak, from the same substance, from the same material, which we can now call energy or universal matter. They are merely different forms in which matter can manifest. If we compare this situation with Aristotle's concept of matter and form, we can say that Aristotle's matter, which was primarily potential, that is, possibility, should be compared to our concept of energy. When an elementary particle is born, energy reveals itself through form as material reality. Modern physics cannot, of course, be satisfied with merely a qualitative description of the fundamental structure of matter. It must attempt to deepen the analysis to a mathematical formulation of the laws of nature that define the forms of matter, namely, elementary particles and forces, based on carefully conducted experiments. A clear distinction between matter and force, or force and substance, cannot be made in this part of physics, as any elementary particle not only generates forces and experiences the effects of forces, but also simultaneously represents a specific force field in this case. The wave-particle duality of quantum mechanics is the reason that the same reality presents itself as both matter and force. All attempts to find a mathematical description for the laws of nature in the world of elementary particles have so far begun with quantum field theory. Theoretical research in this area was undertaken in the early 1930s, but even the initial works in this field revealed very serious difficulties in the area where quantum theory was attempted to be unified with the special theory of relativity. At first glance, it seems that the two theories, quantum theory and relativity theory, pertain to such different aspects of nature that they practically cannot influence each other, and that therefore the requirements of both theories should be easily fulfilled within the same formalism. However, a more precise investigation showed that both theories conflict at a certain point, resulting in all subsequent difficulties. The special theory of relativity revealed a structure of space and time that turned out to be somewhat different from the structure attributed to them since the creation of Newtonian mechanics. The most characteristic feature of this newly discovered structure is the existence of a maximum speed that cannot be surpassed by any moving body or propagating signal, that is, the speed of light. As a consequence, two events occurring at 2 points that are quite distant from each other cannot have any immediate causal connection if they occur at such moments in time when the light signal emitted at the moment of the first event has not yet reached the other point. Such a causal connection can only be considered possible with a delay after the moment of the occurrence of that event, and vice versa, since no influence of any kind can be transmitted from one process to another at one moment in time, that is, instantaneously. Both processes cannot be connected by any physical influence, and therefore by causal connection. For this reason, actions over large distances, as they appear in the case of gravitational forces in Newtonian mechanics, turned out to be incompatible with the special theory of relativity. The new theory was to replace such action with local actions, that is, the transmission of force from one point only to the directly adjacent point. The natural mathematical expression of interactions of this kind turned out to be differential equations for waves or fields, invariant under Lorentz transformations. Such differential equations exclude any direct influence of simultaneous events on each other, and therefore the structure of space and time expressed by the special theory of relativity sharply limits the area of simultaneity in which no influence can be transmitted from other areas where direct influence of one process on another can occur. On the other hand, the uncertainty relation in quantum theory establishes a strict boundary of precision with which coordinates and momenta, or moments of time and energy magnitude, can be measured simultaneously. Since a sharply defined boundary implies infinite precision in fixing a position in space and time, the corresponding momenta and energies must be completely uncertain, meaning that processes with any momentum and energy should dominate with overwhelming probability. Therefore, any theory that simultaneously fulfills the requirements of the special theory of relativity and quantum theory seems to lead to mathematical contradictions, namely divergences in the realm of very high energies and momenta. These conclusions do not necessarily have to be of a necessary nature, as any formalism of the kind discussed here is very complex, and it is possible that mathematical means will be found to help eliminate contradictions between relativity theory and quantum theory at this point. However, so far, all mathematical schemes that have been explored have indeed led to such divergences, that is, to mathematical contradictions, or they have proven insufficient to satisfy all requirements of objectivity. Furthermore, it has become evident that the difficulties indeed stem from the point just discussed. The point at which mathematical schemes lead to divergences does not satisfy the requirements of either the theory of relativity or quantum theory, and it has proven to be very interesting in its own right. One such scheme, for example, when attempting to interpret it using models of real processes in space and time, led to some kind of time reversal. It described processes in which several elementary particles suddenly emerged at a specific point, with the energy for this process arriving only later through some other collision processes between elementary particles. However, physicists, based on their experiments, are convinced that such processes do not occur in nature, at least when both processes are separated from each other by some variable distance in space and time. In another theoretical scheme, an attempt to eliminate the divergences of the formalism was made based on a mathematical process called renormalization. This process involves shifting infinities in the formalism to a place where they cannot interfere with obtaining strictly defined relationships between observable quantities. Indeed, this scheme has already led to a certain degree of decisive success in quantum electrodynamics, as it provides a way to calculate some very interesting features in the hydrogen spectrum that were previously unexplained. However, a detailed analysis of this mathematical scheme has made it plausible to conclude that the quantities that in ordinary quantum theory should be interpreted as probabilities may, in this case, under certain circumstances, after the renormalization process has been conducted, become negative. This, of course, excludes a consistent interpretation of the formalism for describing matter, as negative probability is a meaningless concept. Thus, we have already transitioned to problems that are currently at the center of discussion in modern physics. A solution will eventually be found thanks to the continually enriching experimental material obtained from increasingly precise measurements of the characteristics of elementary particles, their birth and annihilation, and the forces acting between them. If we seek possible solutions to these difficulties, it may be worth recalling that such processes with apparent time reversal were discussed above. They cannot be excluded based on experimental data only if they occur within very small space-time regions, in which it is still impossible to trace the process in detail with our current experimental equipment. Of course, given the current state of our knowledge, we are hardly ready to accept the possibility of such time reversal processes. However, we should not deny the possibility of observing such processes at a later stage in the development of physics, just as we observe ordinary atomic processes. But here, the comparison of the analysis of quantum theory and the analysis of relativity theory allows us to present the problem in a new light. The theory of relativity is associated with a universal constant of nature, the speed of light. This constant is crucial for establishing the connection between space and time, and therefore must itself be contained in any law of nature that satisfies the requirements of invariance concerning Lorentz transformations. Our ordinary language and concepts of classical physics can only be applied to phenomena for which the speed of light can be regarded as practically infinitely large. If we approach the speed of light in our experiments in any form, we must be prepared for results that can no longer be explained in terms of these classical concepts. Quantum theory is associated with another universal constant of nature, Planck's constant. An objective description of processes in space and time is only possible when we deal with objects and processes of relatively large scales. It is precisely then that Planck's constant can be considered practically infinitely small. When we approach the region in our experiments where the Planck quantum of action becomes significant, we encounter all those difficulties in applying ordinary concepts. But there must be a third universal constant of nature. This follows simply, as physicists say, from dimensional considerations. Universal constants define scale quantities in nature. They provide us with characteristic quantities to which all other quantities in nature can be reduced. However, a complete set of such units requires at least 3 fundamental units. The simplest way to see this is from the ordinary agreements on units, such as the use of the CGS system, centimeter, gram, second, by physicists. Units of length, units of time, and units of mass together are sufficient to form a complete system. At least 3 fundamental units are necessary. They could also be replaced by units of length, speed, and mass, or units of length, speed, and energy, and so on. Within the basics, at least the speed of light and Planck's quantum of action give us only 2 of these quantities. There must be a third, and only a theory containing such a third unit may be capable of leading to a theoretical definition. That is, the possibility of calculating the masses and other properties of elementary particles. If we base our understanding of elementary particles on our current knowledge, perhaps the simplest and most acceptable way to introduce the third universal constant is the assumption that there exists a universal length on the order of 10 to the power of negative 13 centimeters. This length is therefore comparable to the radii of light atomic nuclei. If we form an expression from these 3 units that has the dimension of mass, this mass has the order of magnitude of the mass of ordinary elementary particles. If we assume that the laws of nature indeed contain such a third universal constant of dimension length on the order of 10 to the power of negative 13 centimeters, then it is quite possible that our ordinary representation may only be applicable to such regions of space and time that are large compared to this universal constant of length. As we approach regions of space and time in our experiments that are small compared to the radii of atomic nuclei, we must be prepared for the observation of qualitatively new processes, phenomena of time reversal, which were mentioned above and so far only as a possibility derived from theoretical considerations, could therefore belong to these tiniest space-time regions. If this is the case, then it is likely that it could not be observed in such a way that the corresponding process could somehow be described in classical concepts of causality. And yet, to the extent that such processes can be described in classical concepts, they must also reveal a classical order of succession in time. But so far, too little is known about processes in the smallest space-time regions, or what, according to the uncertainty relation, approximately corresponds to this statement at the highest transmitted energies and momenta. In attempts to achieve greater knowledge of the laws of nature that determine the structure of matter, and, consequently, the structure of elementary particles, based on experiments with elementary particles. Certain properties of symmetry play an especially important role. We recall that in Plato's philosophy, the smallest particles of matter were absolutely symmetrical formations, namely regular solids, the cube, octahedron, and icosahedron. In modern physics, however, these special groups, derived from the group of rotations in three-dimensional space, are no longer at the center of attention. What takes place in the natural sciences of the new era is by no means a spatial form, but represents a law, and thus has, to a certain extent, the appearance of a space-time form. Therefore, the symmetries applied in our physics must always relate to space and time jointly. However, certain types of symmetry seem to play a particularly important role in the theory of elementary particles. We learn about them empirically, as their consequences are the so-called conservation laws, as well as through the system of quantum numbers, which can be used to systematically order events in the world of elementary particles according to experience. Mathematically, we can express them through the requirement that the fundamental law of nature for matter should be invariant under certain groups of transformations. These groups of transformations are the simplest mathematical expression of symmetry properties. They serve in modern physics instead of Plato's solids. The most important of these will be briefly listed. The group of so-called Lorentz transformations characterizes the structure of space and time in the hidden special theory of relativity. The group studied by Pauli and Bira corresponds in its structure to the group of three-dimensional spatial rotations. It, as mathematicians say, manifests itself with the emergence of a quantum number that was empirically discovered in elementary particles 25 years ago and was named due to spin. The next two groups, behaving formally like rotation groups around a rigid axis, lead to conservation laws for charge, baryon number, and lepton number. Finally, the laws of nature must also be invariant under certain reflection operations, which need not be listed in detail here. In this regard, research by Li and Yang has proven to be particularly important and fruitful, according to whose idea a quantity called parity, for which a conservation law was previously assumed to be valid, is, in fact, not conserved. All known properties of symmetry can be expressed with the help of a simple equation, understanding that this equation is invariant under all the aforementioned groups of transformations, and therefore it can be thought that this equation already correctly reflects the laws of nature for matter. But the solution to this question is not yet available. It will only be obtained over time through more precise mathematical analysis of this equation and through comparison with the experimental material being collected on an increasingly larger scale. However, stepping away from this possibility, one can hope that through the agreement of experiments in the field of elementary particles at high energies with the mathematical analysis of their results, it may someday be possible to achieve a complete understanding of the unity of matter. The expression complete understanding would mean that the forms of matter, approximately in the sense in which Aristotle used this term in his philosophy, would turn out to be conclusions, that is, solutions of a closed mathematical scheme reflecting the laws of nature for matter. In the history of science, remarkable discoveries and new ideas have always led to scientific discussions. These discussions provoke the emergence of polemical publications, and such criticism is often entirely necessary for the development of science. However, disputes have almost never reached the degree of sharpness that they acquired after the creation of the theory of relativity, and to a lesser extent, quantum theory. In both cases, scientific problems were ultimately linked even to controversial political issues, and some physicists attempted to promote the victory of their views by resorting to political methods. This tumultuous reaction to the latest developments in modern physics can only be understood by recognizing that this development has shaken the very foundations of physics and possibly of natural science as a whole, and that this movement has caused a feeling that the entire ground on which natural science rests is slipping away from under our feet. But at the same time, this perhaps means that the correct language to discuss the new state of affairs has not yet been found, and that imprecise and partly incorrect statements made in a number of cases in the heat of enthusiasm for new discoveries have led to all sorts of misunderstandings. Here we are indeed dealing with a fundamentally difficult problem. The advanced experimental techniques of our time have introduced completely new aspects of natural phenomena into the field of vision of natural science, aspects that cannot be described using everyday concepts or only with the concepts of previous physics. But in that case, what language should they be described in? The primary language that is developed in the process of scientific explanation of facts in theoretical physics is usually the language of mathematics, namely, a mathematical scheme that allows physicists to predict the results of future experiments. A physicist may be satisfied with possessing a mathematical scheme and knowing how to apply it to interpret his experiments. However, he must also communicate his results to non-physicists, who will not be satisfied until they are given an explanation in ordinary language, in a language that can be understood by everyone. But even for physicists, the possibility of description in ordinary language is a criterion for the degree of understanding achieved in the corresponding field. To what extent is such a description at all possible? Can one, for example, speak of the atom itself? This is as much a linguistic problem as it is a physical problem. Therefore, it is first necessary to make several remarks about language in general and scientific language in particular. Language was created by the human race in prehistoric times as a means of conveying messages and as a basis for thought. We know little about the various stages of its formation, but in any case, today, language contains a large number of concepts that can be regarded as a useful tool for more or less unambiguous transmission of messages about events in everyday life. These concepts were gradually developed in the process of using language without critical analysis. It is assumed that some words are used frequently enough. Hence, we know more or less precisely what they mean. It is a well-known fact that words are not defined as clearly as they may seem at first glance, and that they possess only some limited areas of application. For example, one can speak of a piece of wood or pieces of iron, but one cannot speak of a piece of water. The word piece does not allow its application to liquid bodies. Another example, bore, when explaining the limited applicability of concepts, usually tells the following story with great enthusiasm. A little boy comes into a store with a fishing rod in hand and asks, "Can I buy a candy mix for 1 penny?" The seller takes 2 candies from his jars, gives them to the boy, and says, "You can make the mix yourself." A somewhat more serious example of the problematic relationship between words and concepts is the fact that the words red and green are applied differently by colorblind individuals. Although it is obvious here, the boundaries of the application of these words for colorblind individuals must be drawn quite differently than for other people. This fundamental vagueness of the meaning of words has, of course, been recognized for a long time and has led to the desire to provide definitions, that is, as the definition of the word definition states, to establish boundaries indicating where this word can be applied and where it cannot. However, definitions can only be given, of course, using other concepts, and in the end, we must still rely on some concepts that are accepted as they are, without analysis. In Greek philosophy, the problems of expressing concepts in language have been a major subject of research since the time of Socrates, whose life, if we follow its artistic depiction in Plato's dialogues, consisted of a constant discussion of the content of linguistic concepts and the limits of our means of expression to create a solid foundation for scientific thinking. Aristotle, in his logical works, attempted to analyze language and forms and to investigate the formal structure of the process of inference and conclusions independently of their content. On this path, he achieved a degree of abstraction and precision that had been unknown in Greek philosophy before, thus greatly contributing to the clarification and establishment of a certain order in our way of thinking. He effectively laid the foundations of scientific language. On the other hand, logical analysis also brings the danger of oversimplification. In logic, attention is directed to specific linguistic structures, to the unambiguous linking of premises and conclusions, to simple schemes of reasoning. All other linguistic structures are neglected in logic. These structures can arise, for example, from associations between certain intermediate meanings of words. Thus, for instance, a secondary meaning of a word, which leaves almost no trace in our consciousness, can still significantly influence the content of sentences when that word is spoken. The fact that any word can evoke in our thinking many only half-conscious movements can be used to express certain aspects of reality more clearly through language than would be possible with a logical scheme. Therefore, there has often been opposition to such an exaggerated emphasis on logical schemes in language and thought, which could lead to language becoming unsuitable for the purpose for which it was originally created. In natural science, we attempt to derive the particular from the general. A singular phenomenon must be understood as a consequence of simple general laws, where general laws, when formulated in language, can contain only a few concepts. Otherwise, the laws would not be simple and universal. From these concepts, an infinite variety of possible phenomena must be derived, and this must be done not only qualitatively and approximately, but also with a high degree of precision regarding every detail. It becomes evident that the concepts of everyday language, defined as a rule, are so imprecise and vague that they would never allow such a derivation. If a chain of conclusions follows from given premises, the total number of possible members in the chain depends on the precision of the premises. Therefore, in natural science, the basic concepts of general laws must be defined with the utmost precision, and this is only possible through mathematical abstraction. A similar situation may also occur in other sciences. In them, precise definitions may also become necessary, for example, in jurisprudence. But here, the total number of members in the chain of conclusions is never very large, so there is no need for perfect precision. In most cases, a somewhat precise definition proves to be exhaustive, formulated using concepts of everyday language. In theoretical physics, we attempt to understand groups of phenomena by introducing mathematical symbols that can be correlated with certain facts, namely, the results of measurements. For the symbols, we find names that clarify their connection to measurement. In this way, the symbols are linked, therefore, to everyday language, but then the symbols are interconnected through a strict system of definitions and axioms, and ultimately, the laws of nature acquire the form of relationships between symbols. The infinite variety of solutions to these equations corresponds to the infinite variety of singular phenomena possible in a given area of nature. Thus, the mathematical scheme reflects the group of phenomena under consideration to the extent that the relationships between symbols and measurements are observed. These relationships also allow the laws of nature themselves to be expressed in terms of everyday language, as our experiments, consisting of actions and measurements, can always be described in this language. Of course, as our scientific knowledge expands, the scope of applicability of language increases, new concepts are introduced, and old ones begin to be used in new areas in a different sense than when they were used in ordinary language. Words like energy, electricity, and entropy are well-known examples. Thus, we develop a scientific language that can be seen as a natural extension of ordinary language, suitable for newly emerging scientific fields. In the last century, a number of new concepts were introduced into physics, and in some cases, it took considerable time before physicists became accustomed to using these new concepts. The concept of the electromagnetic field, for instance, was already contained in a certain sense in Faraday's work, which later became the foundation of Maxwell's theory. It was not easy and not immediate for physicists, who had previously focused primarily on studying the mechanical motion of matter, to accept this concept. The introduction of this concept was associated with a change in fundamental scientific ideas. Such changes never occur without resistance, as they touch upon the very essence of understanding nature. They cannot proceed easily. Despite this, all concepts introduced into physics by the end of the last century formed a closed system that can be applied to a wide range of phenomena. This system, along with earlier concepts, formed a language that can be successfully used in the research of not only scientists, but also technicians and engineers. The fundamental ideas of this language include the assumption that the sequence of events in time is completely independent of their arrangement in space, that Euclidean geometry holds true in real space, and that processes in space and time occur independently of whether they are observed or not. Of course, no one disputed that any observation exerts a certain influence on the phenomenon that is to be observed, but in general, it was assumed that through sufficiently careful conduct of experiments, this influence could ultimately be made arbitrarily small. This seemed to be a necessary condition for realizing the ideal of objectivity, considered the foundation of all natural science. In this, to some extent, calm state of physics, quantum theory, and the special theory of relativity suddenly introduced changes, initially slowly and then gradually intensifying, to the foundations of natural science. The first intense discussions erupted regarding the problems of space and time raised by the theory of relativity. How should we speak about the new state of affairs? Should we consider Lorentz contraction of moving bodies as real or merely apparent? Should we say that the structure of space and time genuinely differs from what was previously assumed? Or should we only state that experimental results, when theoretically interpreted, must be mathematically linked in such a way that it corresponds to this new structure, while space and time, as universal forms of perception through which we experience the world, remain what they have always been? The actual issues underlying many of these contentious questions stemmed from the fact that there was no language in which one could coherently discuss the new situation. The ordinary language was based on old concepts of space and time, and only this language served as a means of unambiguous communication regarding messages, instrument placements, and measurement results. However, experiments simultaneously showed that old concepts could not be applied everywhere. Therefore, a natural starting point for interpreting the theory of relativity was the circumstance that in the limiting case of very small speeds, speeds that are small compared to the speed of light, the new theory turned out to be practically identical to its predecessor. Consequently, this theory itself indicated how to interpret mathematical symbols, how to relate them to experiments, and how to connect them with the concepts of ordinary language. In fact, it was precisely due to this connection that Lorentz transformations were found relatively early on. In this area, therefore, there was no ambiguity regarding the meanings of words and symbols. In fact, these connections were already sufficient to apply the theory to the entire realm of experiments related to the problem of relativity. Thus, the contentious questions about the real or apparent Lorentz contraction, or the meaning of the word simultaneous, and so on, actually have no bearing on the facts, but concern only language. On the other hand, the relativity of language over time has been recognized, suggesting that one should not insist too rigidly on certain principles. It has always been difficult to find universal criteria for which concepts can be applied in language and how they should be used. Perhaps it is more appropriate and simpler to wait for the further development of language, which, after some time, will correspond to the new state of affairs in the special theory of relativity. Such correspondence has, in fact, already largely developed over the past 50 years. For example, the distinctions between real and apparent Lorentz contraction have simply disappeared. The word simultaneous is generally used in a manner that aligns with the definition given by Einstein, while for the somewhat more complex concept, The phrase "in space" for such an interval has come into use, and so on. In the case of the general theory of relativity, the idea of the non-classical nature of the geometry of real space has been sharply contested by some philosophers, who claimed that the very scheme of conducting our experiments presupposes the validity of Euclidean geometry. For instance, when a mechanic tries to create perfectly flat surfaces, he can do so as follows. He first produces 3 surfaces of approximately equal size that are more or less flat. Then he places each pair of these surfaces against each other in various relative positions. The degree to which mutual contact is possible in all possible positions of the surfaces can be considered a measure of the accuracy with which the surfaces should be regarded as flat. The mechanic will be satisfied with the 3 planes only when the contact between each pair occurs simultaneously at all points. Once this is achieved, it can be mathematically proven that Euclidean geometry must hold on all 3 surfaces. This was the argument put forth by G. Bingley, for example. Our own actions are directed towards ensuring that Euclidean geometry is fulfilled. From the perspective of the general theory of relativity, one can naturally respond that the argument presented only proves the validity of Euclidean geometry at small distances, specifically at distances on the order of the sizes of our experimental setups. The accuracy with which Euclidean geometry holds here is, in fact, so great that the aforementioned process of creating flat surfaces can always be carried out. The exceptionally small deviation from Euclidean geometry that still exists in this area will go unnoticed, as the surfaces are made from materials that are not absolutely rigid and can undergo slight deformations, and also because the concept of contact cannot be defined with perfect precision for surfaces of cosmic order. The described process cannot be applied, but that is already a problem beyond experimental physics. Again, a natural starting point for the physical interpretation of the mathematical schemes of the general theory of relativity is the fact that geometry at small distances turns out to be approximately Euclidean. In this area, the general theory of relativity aligns with classical theory. Therefore, there is a clear connection between mathematical symbols, measurements, and concepts of ordinary language. In contrast, in sufficiently large areas, non-Euclidean geometry may prove to be physically valid. In fact, long before the general theory of relativity was established, the possibility of non-Euclidean geometry in real space was discussed by mathematicians, particularly Gauss in Göttingen. When Gauss conducted very precise geodetic measurements based on a triangle formed by the 3 mountains of Bro, Cannon in the Harz, and Inselberg in Thuringia, he had to carefully verify whether the sum of the 3 angles of the triangle indeed amounted to 180 degrees. He considered it entirely permissible to discover deviations that would prove a departure from Euclidean geometry. However, in reality, he was unable to detect any deviations within the precision of his measurements. In the case of the general theory of relativity, the language in which we formulate general laws corresponds quite well to the scientific language of mathematics, while ordinary concepts are used to describe the experiments themselves, as Euclidean geometry holds with sufficient accuracy at small distances. However, the most challenging problem regarding the application of language arises in quantum theory. Here, there are no simple guiding principles that would allow us to connect mathematical symbols with concepts of ordinary language. The only thing that is primarily known is the fact that our ordinary concepts cannot be applied to the structure of the atom. Again, one might consider the natural starting point for the physical interpretation of the formalism to be the fact that the mathematical scheme of quantum mechanics for distances larger than the size of an atom approaches the mathematical scheme of classical mechanics. But even this statement can be made with some reservations, and for large distances, there are many solutions to quantum mechanical equations for which it is impossible to find an analogous solution within classical physics. In such quantum mechanical solutions, the previously discussed interference of probabilities manifests itself, which does not exist in classical physics. Therefore, even in the limiting case of very large sizes, the connection between mathematical symbols on one side and measurements and ordinary concepts on the other is somewhat non-trivial. To achieve unambiguity in this connection, it is necessary to consider a second aspect of the problem. It is essential to note that the system, which should be considered according to the method of quantum mechanics, is actually a part of a significantly larger system, ultimately the entire world. It interacts with this larger system, and we must also add that the microscopic properties of the larger system are, at least to a significant extent, unknown. This formulation undoubtedly accurately describes the state of affairs. This system could not be the subject of measurements and theoretical investigations if it did not belong to the world of phenomena, if it were not connected by some interaction with the larger system of which the observer is a part. Interaction with this larger system, with all its significant, unknown microscopic features, then introduces a new statistical element into the descriptions, namely, in the quantum mechanical and classical descriptions, which must be taken into account when considering the system in the limiting case of large sizes. This statistical element so thoroughly negates the results of the interference of probabilities that the quantum mechanical scheme indeed converges with the scheme of classical physics. At this point, one can therefore establish a clear connection between the mathematical symbols of quantum theory and the concepts of ordinary language, and this correspondence is, in fact, sufficient for interpreting experiments. What remains are problems that again pertain more to the realm of language than to the realm of facts, as the concept of fact implies that a phenomenon can be described in ordinary language.